Okay. All right. So hello, everyone. My name is Cameron again. We're going to be doing the second session here on Julia for Economists, and it's going to be about parallelization and everything today. So it's kind of a pleasure to have you here. And if we're kind of a small group today, so if you just want to ask stuff, just go ahead and ask and we can figure it out. Okay. So I'm going to share my screen. I'm going to be walking through just a notebook today because Python really sucks and you have to do a lot of stupid Python stuff to get the fancy slides that I had last time, and something happened to my Python environment and I didn't want to fix it in 30 minutes before today. So we'll be going through a slide and it'll be fine. So we're gonna have a lot of fun. Okie dokie. So this is Julia for Economists, parallelization for fun and profit. So we're going to be going through the actually, can we all see my my web page here? I think that's, I don't know.
Yes, we can see it.
Okay. All right, cool. Okay, so just for a brief introduction, if you weren't here for the last one, I'm Cameron Pfeiffer. I'm a finance PhD student at the University of Oregon, and I'm visiting here at the Stanford GSB. I mostly work on kind of asset pricing stuff, Bayesian econometrics, and making computers do stuff is kind of my favorite thing. So this is a good opportunity for me to show how it is that I try to make computers go fast, and sometimes I succeed. Okay. Oh, I also wanted to mention before I get into it, I have a ton of Julia stickers. So if you're on campus, come find me. I'm in the Bass Center, or send me an email and I will give you a Julia sticker, because I have way too many of these accumulated from many Julia cons. Okay, so with the stickers out of the way, I'm going to kind of go into what is this? What is this class? What are you going to kind of learn today? So this is the second in a 5-part series we're doing in winter and spring terms. Don't worry if you missed the first, if you're confused about kind of Julia basics, it's at any point during this lecture, just be what is that thing? And I will go through it because it helps to reinforce things. I'm not going to be mad if you ask about that. And then there's 3 upcoming sessions. One is on optimization and automatic differentiation. So that'll be continuous optimization, and we'll do some integer programming type stuff. Then I'll have a performant programming. So basically how to make Julia go as fast as you possibly can, or as best as I can teach you to make it go fast. And some best practices, right? So how to not ruin everyone's lives when you're writing code for them. Which some people can debate about whether or not I'm actually accomplishing. And then the last one is just going to be about Bayesian inference and probabilistic programming, which I'm super excited about. So those will be March, April, and May, and we'll send out more information about those as we get closer to that. So the general focus for all of these is to be better at research computing, because a lot of research nowadays is quite computational, right? If you work on anything structural, chances are good you're doing some kind of weird, non-standard computational thing that's you can't quite find a canned package to do. So a lot of people end up rolling a lot of their own estimators and code and all that kind of stuff. So I want to kind of express to you ways that you can think about doing them fast and quickly, and write the code so you can get on with your day and talk about your analysis. And I think Julia is a pretty good tool for that. So today we'll be doing parallelization, which is a really good way to make use of all the resources that are inside of your computer. Okay. So I'm going to talk to you today also about your CPU and what's in it, because I think a lot of people have no idea how their CPU works. I only sort of vaguely did before I was sketching out the notes for today. But I think it's important for you to understand a little bit of how your CPU works, so you can understand how it is that we do, parallelization, and why it is that it's sometimes a good idea to use parallelization. I'm going to talk about multi-threading, which is kind of my preferred form of parallelism, at least for small to medium problems, and then multiprocessing for kind of larger problems, which is, this was the first thing that Julia did, going way back when, in like Julia 0.6 or 0.7 or something, it had multiprocessing, but it didn't have multi-threading natively, and it has multi-threading as of Julia 1.3. And I personally find the threading tooling in Julia to be really good, but that's because I spent a lot of time in C#, and the Julia and C# form of multi-threadings is very similar.
Cameron, can you clarify the difference between multi-threading and multiprocessing?
Yes, I'm going to be doing. I'll be like digging into it a little bit, but the head start is that multi-threading is like having a bunch of friends to help you move your house, whereas having multiprocessing is hiring multiple moving companies that each do different things. So multiprocessing is a lot more flexible about what it is able to do. The process, like this.
So things like MPI, are you talking about that?
Yeah, I'll talk a little. I'm not going to talk about MPI directly, but I'll talk about like the constructs that Julia uses to do MPI. So I'm not going to like root around in like kind of the low level kind of stuff, which is a little frustrating, but I'll make it nice and easy. And if we have GPU parallelism at the end, so I'm going to show you how to use like, basically if you have a GPU in your machine, hopefully an NVIDIA one, there is support for AMD GPUs, but it's like not as good. I think that's generally the case in a lot of places. We'll talk about that a little bit. So there's going to be 3 types of parallelism that I'm going to talk about here. And you'll know how to use them at the end of it. And if there's time, I have a little bit of a project, but we didn't get to it last time. So I'm not super hopeful that we'll be able to do the project. Okay. The kind of procedure for today is I'm going to do 50-minute lectures. I have a 10-minute breaks at the top of the hour, but there's a 15-minute break at 11. So there's a little bit of a longer one if you want. I would prefer if you interrupt me if you have questions. But if you don't want to talk or you can't talk, then type them in the chat and Natalia will interrupt me. And Natalia is also a super pro, so we're like glad to have her here because like she understands this. And I'm like a programming by vibes person, so this will be nice. And I'll have some intermittent concept checks for you to basically like sit down and like type out what it is that I've told you. So there's, I think there's like 3 or 4 of them during the course of this lecture, and they're fairly small little projects, where you can kind of tinker around with various forms of parallelism. Okay, so please interrupt me. The second you get confused, I want to stop and correct that, especially since there's kind of a small group. So, I'm perfectly happy to be interrupted. Okay, any questions so far in any of this? Basically, there's like, admin stuff. Okay. All right, so I'm assuming that you guys have a Julia installation. So the Julia binary, and it's like linked correctly and installed or whatever. I'm assuming that you have a text editor. So VS Code is recommended. That's what I'm going to use. But you can use whatever you want, and your big beautiful brain. So if you do not have one of these, please take a moment to go get them. And if you don't know how to go get them, please like put something in the chat. And your big beautiful brain is already attached to your head, so you don't need to go anywhere to go get it. And don't be like, I don't have one. I'm stupid. This is hard. I'll kick you out of the room for lying to me. Okay. So is there anybody who needs to go install this? Like, type this in the chat. Okay. All right. Okay, so I'm going to give you some warnings. So the first one is I learned a lot of this informally. Like parallelization is, if you go through the CS route, you learn a lot about kind of the nuts and bolts of it. And you kind of have a good, I get the sense that people who learn this formally have a very good understanding of kind of why it is that the rest of us normies have heuristics for why it is that certain things in parallelization are a terrible idea or great idea or so on. So I have a ton of heuristics for when it is appropriate to use some kind of parallelization. So I'm going to try and give you the rigor as best as I can. but you're not like, this is not like fancy CS professor Cameron is doling out information to you. This is like, I'm going to give you like short bullet points about when it is generally appropriate to do various parallelization methods. And I'll kind of try and show you why. So if questions come up that's like about rigor, you know, like hopefully I can answer them, or like hopefully Natalia knows the answer. But this is going to be what I call a folksy introduction to parallel computing, where I'm just kind of going to communicate as best as I can what I know. All right. That leads me to kind of the second big warning here, is that parallelism is often a foot gun, meaning it's a really, really, really good way to shoot yourself in the foot if you do it stupidly and if you do it flippantly. If it goes wrong, multi-threading or multiprocessing or whatever method you're using, you can get all kinds of crazy stuff happen that you don't understand and may not even notice. So best case scenario, it's just harder to debug parallel code. You'll pull your hair out if you're not doing it correctly. So my recommendation is write serial code first and then add parallelism if you think it's needed, right? This is a thing that you add on later if you really need the extra oomph. It's not something you do at the start. Worst case, your answers are silently wrong and you don't even notice it. You could crash your machine. If you're like, I want 70,000 threads and I want them all to be doing this thing and your scheduler sucks, you can crash your machine. Fun fact, I actually crashed an entire company's Citrix server because I spooled up way, way, way too many threads by accident and made them all not yield to each other. So I basically did some pretty bad stuff, and you may too if you're not paying attention. So I'm going to help them try to give you a sense of what the danger inherent in parallelism if you're not paying attention. So it's a dark art. Like this is like a defense against the dark arts type situation where, you know, it's handy. It's a very, very good tool to have, but it's, you know, it is not an all-purpose tool. And so you should use it cautiously and wisely and think very carefully about when it is that you choose to add some kind of parallel component to your code. Okay. But
is there parallel debugger for Julia? Like sort of like Intel Parallel Studio for C or Python?
Not a great one. There's like some annoying things where if you're doing like multi-threading and one of your threads throws an exception, then the other threads don't necessarily respond to that exception. And you can still have continuations on the other threads, and sometimes it's a little hard to track down. But at the very least, if you throw exceptions on, you know, a process or a thread, you can get an exception out of that and understand why. So it's basically like call stack debugging for the most part. So if you wanted to like really root around and have like a good debugger, it's a little challenging. But for the most part, I found like kind of the high level programming tools of Julia. Julia is like multi distributed compute type stuff to be pretty easy to use. Like I haven't needed like a big debugger yet. Fingers crossed. But today we're just gonna like go crazy and just kind of break some stuff, and it's gonna be fun. So don't worry about today, but in your code, be careful, especially if you're doing something that's meaningful. Okay, any questions or comments or concerns about any of that? All right, cool. Okie dokie. So now we're going to leap into how it is that your CPU works at kind of a high level. I'm not going to like root around into the stuff. I'm going to point at a couple of bits, and you'll kind of have to take my word for it that there's like a lot of other complicated stuff that's happening. Right now, I just want you to like sit back and enjoy how amazing it is that your computer works and how it works. Okay. So you may or may not, you have probably everyone has a differing understanding of how it is that their computer works. You might be aware you have some components in it, like there's like RAM, and that there's like a hard drive, and that there's like maybe a motherboard. And you may or may not understand differing degrees of how those things work. And they all do some kind of magic. And the CPU is one of the more magical ones, because it, first of all, it does like most of what you're, like the actual computation of everything that happens inside of your computer is done by the CPU for the most part. And they're really fast. They're really well designed. They're kind of really beautiful pieces of kit. And it is a super magical tool, and I love it. And the way you can think about a CPU is as a fancy box that accepts two things. It accepts instructions, which is what to do. And this is like machine code. So you can think of this as a function. So for example, there might be machine code or binary code that you have for the sign function. And then you have data for those instructions. So for example, the number 17, that is data. And if I have instructions and data, sine wave, the sine function, and the number 17, I can have my CPU actually output the answer to the sine wave function at 0.17, okay? So this is kind of typically how you think about how CPUs work. They just have two little inputs. Basically, you can think of them as like a, there's two little things you pour instructions and data into, and then it just hits the instruction. It just hits the data with whatever the instruction is available is. Okay. Okay. So these fancy boxes have, you know, if you were to open them up, you'd see a couple of things inside of them, right? So there's the control unit, which does a bunch of stuff, but you know, you can think of it as kind of interpreting binary code and putting it into timing and control signals, right? Because these are electrical, you know, in nature, so they kind of have to do a lot of like electrical jiggling to make the stuff inside of your processor actually do stuff. And so the control unit is responsible for that kind of stuff. The arithmetic logic unit, which is called the ALU, is the thing that does the math, right? So if you want to add 15 and 10, it has all the operations that you need to do on the binary representations of 15 and 10 to add them together. And then once it computes those, it dumps those into onto a conveyor belt, basically, that passes it off. There is the cache. And a cache, if you are familiar with how RAM works, RAM is like short-term memory that goes away when you turn your computer off. It's meant to be, you know, written to very quickly and overwritten. It's just like kind of like a big worksheet to store the various intermediate values. The cache is a much faster version of this that is much, much closer to the actual core processor. So the cache is like just like a smaller version that is super fast that you can use, the CPU can use to store intermediate values. Okay. It's also how data and instructions are, where they're stored when they're piped into the CPU. And then there's registers, which are like kind of like little tiny caches. They're basically pointers to instructions in the cache, I believe, that that the ALU can get to directly. So I have this little diagram here that I thought was super helpful. I won't let me scroll out too much, but here's the ALU. This is like the little math bit. It has registers for various things that you feed into it, right? So this would be 10. You'd put 10 inside of the register here. You'd put 15 inside of the B register. The instruction register would have the sum operation. So please add A and B. The ALU would run those, would combine the two inputs that it has, 10 and 15, across the instruction sum, dump it in the accumulator, and decide what to do with it, and eventually pass it on to back to the cache. And it may work its way back into main memory. And the important thing that I'll talk about a little bit more is that there's three caches basically in most processors. There's like, you know, you can have certain processors that have lots of other caches that do different things, but generally you have an L1 cache, which is, I'll talk about in a little bit, that is like small and fast. And then you have L2, which is much larger and a little bit slower. And then you have an L3 cache, which is like, it has like various special functions to make L1 and L2 go faster or work better. Okay. So these are where you store instructions and data. And then you see the control unit and the clock and all that kind of stuff. This is like kind of like how you jiggle the electronics, in your processor to make them do stuff. Okay. All right, so this is kind of just a rough sketch of what the CPU is like. And there's tons of more little bits in here that it's not important to know about, at least for us. Okay, any questions about this weird diagram? Or like what I've told you so far about the CPU? Okay.
Sorry, I've got a question.
Yes.
Can you just give an idea of what should we be paying attention to here? Like other than just knowing that these different things exist?
Okay, so the thing I want to mostly pay attention to is the cache. So the cache is super important because just pay attention to the cache bit, and I'll talk about it when I get to cache misses, which I think is kind of like one of the bigger issues. Basically, I just kind of want to give you like a sketch of what it looks like from a top level, but the cache is important.
Sounds good.
Okay. All right. So CPUs are actually multiple. A CPU, what you hear as a CPU is actually an integrated circuit that has multiple versions of this bolted onto it. So if you have a quad core processor, you have something very similar to this replicated 4 times. Some resources are shared. I believe typically in some cases the L3 cache is shared, but you may have multiple replications of this bolted into the same CPU. Okay, so when you hear a core, you're basically saying I have multiple unique different things that have their own memory. They may have their own control unit. They may have their own kind of stuff like this. Okay. So multiple cores, importantly, can do different things, right? You can have one core doing one thing that does not depend on the other core at all, right? So typically, you might have a bunch of operating system processes running on, one of your cores, and then like if you're playing a video game, maybe it's like, heavily focusing on using the resources available in one core.
Sorry, so just to clarify, so the picture that you showed us, all of those components are usually part of one core. That's like one entire CPU. Okay.
Yeah, with the exception of like the L3 sometimes, depends on your processor type. But for like, at the very least, you will have one ALU per core, typically. And the registers, accumulators, things like that will go along. If you have an Intel, actually AMD has this too. If you've heard the word hyperthreading, more or less that just means you have two sets of data and instruction registers, basically, for the same ALU. And so each of those cores just have more little tiny registers, but for the most part, most of this is replicated for all cores. And I think for our purposes, it's easier just to think of like, take this whole thing, copy paste 4 times for a quad core, at least for all intents and purposes. Okay. So I want to talk a little bit about the cache. So the cache is super short-term storage for instructions, things to do, and data, things to do them with. So it has this kind of hierarchical structure to it. So L1 is the fast cache. This is like the thing where you're like putting stuff that you like using a lot, or that you're queuing up. You know that you're going to call instruction 1 and then instruction 2. And then instruction 3 is probably in the L1 cache if you have like a pipeline processor that's doing a really good job of queuing up resources. Okay, so the L1 is crazy fast. Like this is a very, very fast form of memory. But it's also fairly small, right? It's meant for like, stuff that you kind of use a lot or very frequently, like recently used data, that kind of stuff is stored in the cache. Then you have the L2, which is bigger, but it's slower, right? So typically you can, if you have a bunch of data that you're going to need at some point in the future, or instructions, but but you don't need it super soon, or it just hasn't been requested yet, it may be in the L2, right? And so the L2 is like a place to store things that are that you just don't need quite so much, but it's bigger, so you can store a lot more in it. Okay, and then there's L3, and I spelled this incorrectly. Ignore that. And L3 is kind of like specialized. It has like various features to make L1 and L2 faster, but it also functions as a cache. So it's like, I'm not going to go into the L3. It's kind of like, it's complicated. It varies a lot by processors. And to be honest, I don't quite understand exactly all the little fiddly bits that it does to make things better, but it's there. Okay. So this is the important thing. So when the processor needs something, what it'll basically do, if it needs instructions or data, it'll ask the L1 if it's in the L1. And so you're like, I was supposed to be calculating the sine function with the input 17. Do you have the number that I'm supposed to be using sine on? It'll ask the L1. The L1 says, if it says yes, it'll just give it 17. If it says no, the processor has to go back and ask L2. And L2 is a little bit farther away. You have to do a little bit of a longer walk to get to L2. And then the L2 is also a little slower. So you say, hey, L2, do you have the number 17? And if L2 says yes, it'll give it to you, albeit a little slower than the L1 would. And then if L2 says no, it'll say, oh crap, either I have to ask the L3, and the L3 may not have the number, in which case you have to go like way far away and ask RAM, hey RAM, do you have this number? And that gap in between the cache, which is inside of the processor and really fast, and the RAM is huge. You really, really, really don't want to go ask RAM because that's pretty slow. It's not super big deal, but this is what is called a cache miss. When you ask for something, you check to see if it's in the cache, and if it's not, you have to keep stepping up the ladder of various little bits of memory. And this can really slow stuff down. It's not the biggest issue in the world, but it can be. And I'll talk about this a little bit more. But I want to give you a sense of like how fast the caches are. So this is, I dug this up from my processor. The L1 cache is about 0.8 nanoseconds. I believe this is, round trip query to an L1. So 0.8 nanoseconds is pretty fast. And that's good because you do a lot of L1 cache trips all the time. This is like one of the more frequent ones that you do. The round trip for me for an L2 cache check is 2.4 nanoseconds. And then the L3 cache is way fast, way slower than that, right? That's 5 times faster, 5 times slower to go ask to the L3. And then if you want to ask main memory, that's 14 nanoseconds. That's super slow compared to 0.8 nanoseconds. And the important thing about this stepping down the ladder, asking the L1 and then the L2 and then the L3 and then main memory, is that you have to do all of these. You do 0.8, then 2.4, then 11.1, then 14. And you kind of have to add all these together. And so it gets really slow. So big round trip questions to check to see where data or instructions are in your cache or in main memory can be very costly. So this is called a cache miss. And they can be costly, but they're not always. So as kind of a side note here, you may have heard the word vectorization. If you come from R, right? If you're like an R person, somebody has probably told you something like loops in R are slow, which they are. So you should kind of vectorize your code. And there's other things happening in the R world, but kind of one of the reasons for this is that if you have vectorized code, which means one instruction and a lot of data, you don't have to keep multiple instructions in your cache. You can keep one. And so you can just put that one instruction in your instruction register and just pump data through these A and B registers right here, and you just keep everything constant here. And what that does is it frees information, it frees up space in the L2 instruction cache and the L1 instruction cache and the data cache, right? So vectorization is really nice because you can basically say, I want to do one thing and I want to do it with all of these other things. And then you don't have to, link up instructions and data and just kind of iterate through them together. And Julia, vectorization is not such a big problem because it's, the compiler is pretty good at kind of handling multiple and, single instruction, multiple data type processes. So yeah, but vectorization important sometimes. All right, any questions about this stuff so far, vectorization? Okay, and then just kind of the last part.
Sorry, Cameron, quick question about vectorization.
Okay.
You're calling it vectorization, but is this the same, is this just like in functional programming, anytime you can write something in the functional, like in a map operation, that's basically the same thing?
Yes, that's yeah, in Julia's version of yes, I'll answer that with a yes, right? So map means do this one thing to these many things. That is also a form of vectorization. The implementation between different languages about like how map works is a little trickier. Like in R, what's referred to commonly as vectorized code is like you actually have vectors and vector operations on those on that data that kind of benefits from little bits inside of your processor that's like, yeah, I'm gonna stay
okay. So but another question. So the emphasis that you put was on the L1. So the idea is that when you can signal to the processor that this is some sort of vectorized code, what that does is it keeps it from needing to go to L2, which it does by default otherwise. Is that the idea?
Yes. Yeah. And then to L2, L3 main memory, so on and so forth. So you kind of want to keep your L1. You want your L1 to have a clean pipeline. Okay.
And so is there any limits to how you can do that? Like it's just like anytime you can signal something's vectorized, that by definition means it's simple enough to keep an L1 and it won't run out of memory, or can it still run out of memory?
So it can run out of memory, and that's fine, right? So sometimes your L1 is just not big enough, right? Like if you have a lot of data, that's fine, that's perfectly normal. But what you can do is, when you specify a vectorized function, right? So if you do this, right, xs is equal to 1, 2, 3, and then I do sign.xs. So remember, this dot notation here means please broadcast. This is a vectorized operation. And what happens here is your processor is generally smart enough to pipe in 1, 2, and 3 in sequence. So if you go as your logic unit is asking for 1, that clears up some space in the L1. Right? If you have like kind of good code or a smart processor, you can do that kind of stuff and start piping, and then you can start piping 2 into the L1 so that it's ready the next time that it has to go through and do a loop, right? So this is kind of a simplification of it with like very small data, but yeah, in general, I don't think you should worry. Like the thing I want to communicate here about cachemisses that are a little dangerous is when you're doing a lot of stuff that's using the caches, they're all competing for a shared resource. So if you're multi-threading on the same core and one thread is off doing totally different stuff than the other thread, they can be competing for the same data and instruction space. And so they can crowd each other out, and thread 1 can like use up a lot or all of the L1 cache. And so thread 2 has to keep doing all these cachemisses to go ask L2 or L3 and so on and so forth. So there's a shared resource component here where everyone can kind of crowd each other out, especially in a multi-threaded case. Okay.
Can I ask a question, follow up there? So you were referring to R, and maybe you'll talk about this later, so you can just defer the answer, but like, is the point of the reason why Julia loops are so fast versus R loops being so slow is R is really dumb about like optimizing what goes into which caches, and Julia compiler does a better job of like when I write, if this code that you have here with the sign, right? I could have just written for I equals 1 to 3 sign print your sign of x or whatever, or sorry, sign of I, and like that's equivalent to this, right? Essentially.
I don't know if the lowered code is equivalent, but it's pretty similar. Like they're very similar in terms of, you know, when I say lowered code, I mean like the low level compiled code. But my instinct would be that it is the compiler, right? So R is not compiled. R is interpreted sort of, like you could argue that it's like sort of compiled because a lot of the stuff is like written in like compiled languages. But the actual like R itself is interpreted. So it doesn't have this like ahead of time intelligence about what it is that you're going to need and when you're going to need it. So when you pass Julia code to the compiler, which is LLVM, then like the LLVM can write really good machine code because it knows that, hey, you're going to be doing sign and you're going to be doing it on these 15 things exactly. You know that the return type is going to be float 64 because we can like heavily type all these functions. And so it can do like a lot of clever tricks ahead of time. I think there's also some processor magic that happens. And the processor magic is the stuff I don't quite understand, right? Because like Intel has all this like smart caching stuff where they can kind of shuffle stuff around that I also don't understand. So like in general, my response would be Julia is just in time compiled, which makes it just a bit smarter than R. So you don't need to do all this stupid vectorization stuff, which explicitly tells R, you know, you have an exact framework for this code because it's vector, right? You know what to do with vectors. And so you don't have to like hold Julia's hand about when you have a single instruction and multiple data type operation.
Gotcha.
Yeah. Okay. Other questions? These are rocking. I'm digging this. Okay. All righty. We're out of time. Okay. But in general, I don't want you to like think about, oh my God, am I like hitting? Am I like running out of memory in the cache? It's important. But the way you can kind of think about doing this is just writing good, clean code. And I'll talk about some heuristics that I think will help you a little bit with this a bit later. But you know, these are important, right? These are important sources of latency.
Sorry, Cameron, you said cache miss. Does that mean that what happens when it runs out of memory is that it just skips what you're like skips an iteration or something?
Cache miss is the process when you ask the L1 says I don't have it. So anytime you ask a cache and the cache doesn't have what you're asking for, you have to go back to home base and then report back to the next cache. That's a cache miss. Anytime a cache says that they don't have exactly what you're looking for right now. They may later, but basically you just kind of have to walk up this ladder, which is a little annoying.
Okay. So sorry, so do you need to, does that all happen on the level of the compiler? Like do you as the coder have control over how misses are handled or not? So
no,
much?
you that's at the processor level. That's a super low level operation. What you can do as a programmer is like make sure that things are consistent. So like typing functions, for example, like making sure that if your function accepts a float 64 as an input, it had better return the same type every time. So if it takes a float 64 and it returns float 64, that's one instruction. That's a very cleanly defined function. And the lower, the compiled code for that is super simple. If you have float 64 and then like half the time it turns float 64 and half the time it turns a string, that's a problem. That's like two different, those are, that's a very complicated and different function. And
sorry,
so that instability.
Just to push back, what you're saying is that if you make those instructions simpler, then you make it more likely that the cache misses will get handled. So like the typing example.
That you won't have cache misses.
It sounded like the typing example issue was that like the processor has to do lots of like the extra step of figuring out what type it's dealing with each time it tries to run the function, and that like creates more opportunities for flukes. Is that the idea?
Yeah, so the idea that there is that you need different instructions for different output types. So if you have functions that are type unstable in a Julia world, is what that refers to, where the type is not determined by the type of the inputs, the type of the output is not determined by the type of the inputs, you require more stuff that is instructions to be in your instruction cache. And when that happens, you kind of push other stuff out that might be data or other instructions. And so when you're filling up the cache with more and more complicated functions to handle different stuff, you have to go back and forth and kind of wait. You're more likely to ask the cache for something that's not there because it's full of all the instructions to handle different things. I don't know if that helps.
Yeah, that's helpful. So it sounds like types in particular are a major issue, whether you like explicitly handle them with extra code or you implicitly handle them by forcing Julia to figure out what to do.
Yeah, like type stability is like the #1 speed thing in Julia. So if your code is slow, it's probably a type instability issue. There's various other things, but in general, the compiler is pretty good at, handling the stupid crap. The best thing that you can do as a programmer is write good, clean, high-level code so that you can let the compiler do its job and kind of streamline everything when it hits the processor. So we're working in kind of an upstream level. Okay. All right. So this is kind of like the internals I want you to have in your head. Okay. So I'm going to start here talking about serial processing. So serial processing is what you do by default. When you don't write any special code, at the most basic level, your CPU is like a serial tool. And when I say serial, I mean, it does everything in order and it does everything non-concurrently. So non-concurrently means that like, I don't have threads, I don't have other processes, you kind of have to request that those things exist. By default, it'll go through every single thing one at a time, and it has a very long list of tasks to complete. Okay, so I'm going to show you what it is that serial looks like. So when we start getting into a parallel kind of universe, that you'll understand what the difference is. Okay, so let's say I ran this code here. All right, so basically I'm saying create an X, set it to 0, make a for loop that says I in 1 to 2. So we're going to have I equals 1 and then I equals 2. And then I'm going to do this component here where I just, take X and then I increment it by whatever I is. So you can probably look at this and say, well, what's 1 plus 0? And then what's 2 plus 1? You'll know at the end of this, X is equal to 3. Right? And I can unroll this code into kind of an equivalent representation where I just, you can look at this and see that X is 3, okay? It will always do it in this order, right? This is like, this code is, there's nothing else happening here. It is a list of instructions and you're going to go through each element of this list in order. Nobody's jumping ahead and running 3, the third line, and then the second line. In this case, in this example, it doesn't really matter that much. But here, nothing's jumping around. It's, we can predict this. And I call this is deterministic code, right? So serial processing is like, you can have a little bit of this with like parallel processing, but serial processing is like really, really, really deterministic. You always know what's going to happen because it is like very procedural, okay? CPUs are super fast at this, right? Having single instructions and just like going through and doing each of them in order is exactly what they're built for. And they're very, 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 very good at doing it. It's why your computer runs really fast. It's why like mine's super fast because it can do all these serial operations really, really well. And there's like kind of lots of hidden benefits of this, right? That like explicitly serial, reserving a core to only do really basic serial processing has like lots of kind of really nice properties, right? That The cache is super well built to handle very linear trajectories of code programs. And so it's just, there's lots of little fun bits that you can get from doing just explicitly serial processing. So when you write code, by default, you're writing serial code, at least at the high level. Some functions call multi-threaded operations on the back end. Like if you call anything that's like written in C, chances are good, or Fortran, sometimes those are parallelized at some degree underneath the hood. Okay, so, but if you write any Julia code by default, it is explicitly serial. Okay, you have to do work to make them parallel and or concurrent. And sometimes it's a lot of work, sometimes it's a little bit of work. Okay, so this ordered nature of serial code is good and bad, because you have to wait for unrelated tasks to be completed. So for example, let's say I have this function here, f of a and b. And all it does is it pre-allocates x is 0 and y is 0. It'll go for I in 1 to 10. It'll add to x, it'll increment x by whatever a is times I. So it'll add to x for the first iteration of this loop, a times 1, and then a times 2, then a times 3, so on and so forth. And then it'll also do the same for y, but with b. And then it'll just return x and y. And you'll note here that x and y don't depend on each other, right? They don't, like, why is it that I'm waiting for x to finish before I do y? In principle, you could kind of like do both of these at the same time because I have all these cores and threads and stuff. Like I don't need to wait for x to happen. I can do y also. Of course, this example is really stupid because these operations are very cheap, right? It's not usually worth it to spin up an additional thread to handle this computation at the same time as this, just because like managing the administrative task of managing an additional thread or process is generally quite high. Okay, so this is an example of like maybe a case where if this thing to the right was really expensive, you might want to like actually kind of sidestep it and go do something else while this operation is completing. Okay. You could also even factorize this into two separate functions, right? Because x and y have nothing to do with each other. The only thing they're connected through is y, right? You might not want to run this I loop twice. Okay, but in general, this is a cheap function and these are cheap lines. So maybe no need to parallelize here, but you can kind of get my point where, if this took 5 to 10 minutes and this also took 5 to 10 minutes, if I run them at the same time, I only have to wait 5 minutes, not 10, more or less. Okay. Does this example make sense to people? I know it's a little, here, let me do this costly thing. Yeah, I'll add this to make it explicit that, this is some expensive, costly function of a and b. And you can imagine that this is a function that just like takes forever. Okay. So an example of where like this kind of costly thing can be a pain in the ass is if you're doing lots of expensive things all in order. So for example, what I'm doing here is I've written this expensive function here, and all expensive does is it just generates a big old matrix of random normal numbers. And so this is 10,000 rows by 100 columns. And then all it does is multiply them together, right? So it makes a random matrix and it multiplies them. We can even make this even more costly if you wanted to by just like inverting it also, because inverses are fairly complicated or fairly intense. Okay, and then I have a function called go, which all it does is it calculates an A matrix, which is, this inverse x prime x, and then B, which is just another random inverse x prime x matrix. And then it's just going to add them together. So if you look at this, this is serial code. What it's going to do is we're going to call go. It's going to calculate A, when we have to wait at this line, and we're going to calculate B, and we have to wait for this line to compute, and then we'll just return their sum. Okay. So I have this benchmark macro here. Anytime you see an @ symbol in front of a word, that's called a macro. And it's like a little extra tool that you can use to kind of do various interesting things. I'll probably talk about these in the like, best practices tip. This is like kind of an advanced thing, at least as far as writing your own Go. But we're going to use them because they're handy. The @benchmark macro comes from benchmark tools, and it's a way of finding out how fast it is your function takes to run on average. So what benchmark is doing right now, this whole cell is running, is it's going to run the go function several times, and then it's going to check to see where it is. Okay, we got some results here. Okay, so it'll give us a median runtime, which is 14 milliseconds. 16 milliseconds here is our mean. You can kind of see the histogram here of when it is that it took, how long it took to run. But part of this is just because this is so slow, right? Like, it's really expensive to do it, to draw all these random numbers and then multiply them together and then calculate the inverse, and then we have to do it twice, and they're done at different times. So like, you can imagine if this, if these take minutes or hours, you really don't want to double your time. You just want to, you want to say, hey, go get me A and also go get me B. And then when you guys have them, let's reconvene here and add them together. You want to be able to dispatch these to different processes, different cores, so that they can do all the work that they need to. Okay. Do people understand why it is that we might want to parallelize this? We want to run them side by side so we can wait less. Okay. So I'm going to start talking about multi-threading and multiprocessing. Okay, so there's kind of two ways of achieving some kind of parallelism. So the first one is multi-threading. And you use multiple threads, one or more threads, as part of a process. And a process is like a thing on your computer that is organized around completing some kind of task. So when I start up Julia, for example, actually here, I'll show you what it looks like on my machine. So for example, if I type out, can you guys see my black windows here? So if I run this is my system monitor here. Each of these are different processes. So for example, if I went and started up a Julia process here, we can probably end up finding it down here. But here's like all the other things. Like this is like, these are various things this is like a process that manages my windows. So if I wanted to like do this is the process that handles that. It is like a little manager for various bits of your computer. Julia, when you start up Julia, it puts everything in one process by default, but we can add more if we wanted to. Okay, so when we add threads to that, we're basically taking a process and we're saying, we're going to organize a bunch of tasks under different threads that share memory. So all threads share the same memory. So if I put 16 threads on one process, each of those 16 threads can do different things, but they will use the same cache. Okay. Multiprocessing is where you just say, I want many processes that all have their own memory. And they may or may not have multiple threads. So you could have, 4 processes, each with 16 threads, if you wanted to. And processes will just kind of float around to whatever core is available, but they'll have their own memory footprint as needed. The common line here, the common like party line, is that multi-threading is cheaper and lighter, especially in Julia. The threading is like pretty lightweight. But multi-process parallelism is more general and extensible. So like multi-threading, you're typically like, you're not limited by the number of cores that you have in your machine, but it's a good idea to not exceed the number of cores you have in your processor. So like, on my machine, I've got 16 threads available, so I don't really want to go above 16 threads. It's kind of, you run into decreasing returns to scale. Processing, you can just, spin up a bunch of processes. They may or may not work well because they're still competing for the same resources, but you're not kind of running into the same issue. The system scheduler will handle the processes better.
Sorry, so you have, you said as many, don't choose more threads than you have cores. Does that mean that when you choose a thread, it automatically gets assigned to a distinct core?
Technically, they can float. So everything kind of floats around, but like I believe, actually, I don't know if Natalia knows this a little bit more. I believe they get like fixed to like certain cores for certain procedures.
I think you can bind threads to cores in your code, but
yeah. Oh, that's right. But at least in Julia's scheduler, I think just kind of lets them roam. So it doesn't care so much. But at least processes can flit around. But those two you can bind, I guess, as well.
The operating system is in charge of that stuff typically, right?
Yeah, the operating system is in charge of processes, whereas Julia is in charge of threads.
Oh, interesting. I thought also thread assignment to cores was managed by OS.
Oh, thread assignment to cores, yes, but like the actual control of when a thread is like told to do something.
Yeah, no, of course, yeah, that's all, yeah.
Yeah, like Julia handles like, hey, thread 4, please go do task A. Whereas the processor says, hey, I really want to do task A. Can you please let me use the resources? And the operating system will say, hey, yes, go ahead. But yes, so I generally prefer to multi-thread just because it's a little bit easier of a programming paradigm. When you work with multiple processing, yes, it is much more general and extensible, but it can be, multi-process programming can be a little bit harder to write good code for, just because they have different memory spaces. So you have to ask them to talk to one another, and you have to build infrastructure to get them to talk to one another. And that infrastructure is a little annoying to build. Okay, I think this is probably a good time to stop for our 10-minute break.
Any chance we could go any chance we could go for 10 more minutes?
2 more minutes?
10 more minutes and then break then.
There's a question in the chat, so maybe you can address that.
Let's see here. Yes, spinning up multiple processes is a lot more expensive as well. Yes. However, typically what you do when you're doing some kind of multi-process programming is you create a bunch of worker processes at the start of your program, and then you just never ask them to go away. Threads have short lifespans, right? They can kind of come and go and live and die. And when you kind of spool them up, it's a little bit costlier. But once the process is there, you can just ask it to do stuff. And it's just a matter of kind of sending them a message to ask them to do stuff. So yes, they're both costly, but getting threads to do stuff is faster.
I think one note is that in multi-thread parallelism, you can't exceed your machine. Like there is no way I can talk outside of the boundary of my CPU. And in multi-process, I can actually jump to a different machine, physical machine, with other CPUs.
Yes, that's a good point.
Yeah.
Oh, I like that. Actually, I didn't get the chance to talk about like cluster managers. Like Julie has a really good cluster manager. So if you want to if you have like really big cluster computing, and you're in kind of a multi-process type environment, you can have like hundreds of thousands of processes and have really good communication between all of them. So,
sorry, I'm still confused about what the difference is. Like I understand that like at a high level from the programmer's perspective, there's some difference in sort of how much you have to specify or something like that. And then there's a difference in terms of whether it sounds like threads can float, but processes are more fixed. So maybe I'm just
they both, I would think of them as both floating, but threads as being like quicker on the draw. So like threads are like things that you can they're always ready to go. They're always ready to do stuff. Whereas processes, you have to like tie a piece of string to a pigeon's leg and like send it off, and then like hopefully the other pigeon gets the, hopefully the other
Yeah,
process
so why,
gets the pigeon.
so why would you ever want to do multiprocessing? Is it just much faster if you have a very particular, like a
'Cause you can do
difficult
it.
task?
You can do a ton of them. Like you can do like thousands of processes, and
I
the
see.
system is really like your operating system is like perfectly equipped to handle all of this
Oh,
and
I
to
see.
like
So this is-
schedule resources as needed.
Like if you want to run on the entirety of Sherlock, you'll have to use multiprocessing. Like
Got it.
to take over the 1,000 machines,
Got it.
Yeah.
Okay. So is this the right way to understand it? Like when you do multi-threading, you're sort of saying like, I'm gonna assume that I'm basically gonna take the whole core, because it's gonna be very complicated to allocate space within cores optimally. But if I do multiprocessing, then I specify exactly how much I need for any particular task. And so I can send it out and know that even if I send out lots and lots, like my first process is gonna occupy, like a fifth of one core, and then my next process is gonna take up another 2/5, and I can just like max out that way. Is that the idea?
You can max out both, right? So threads. So if I spool up 16 threads on my machine, all those threads will operate on it'll push those threads out on different cores. So I can, in principle, occupy all 8 of my physical cores with hyperthreading at 16, and just kind of
So then why is it that you need multiprocessing to handle, to like spread things around Sherlock? Why don't you just send threads around all of Sherlock?
because the threads are handled like in machine. So if I have
they all share memory, so you can't share memory across nodes. It's like localized to the machine.
Yeah.
The threads share memory, or the processes share memory?
Threads threads share memory, but like processes, they can do whatever they want. They have their own RAM that they can talk to, and kind of do all the compute stuff. But good question. Okay. All right. Why don't we take a break here, and we'll go to 10:10, and then we can pick up there. Is that okay with everyone? Okay. Excellent. Okay, welcome back, everyone. We're going to continue here. We had some good questions on the break, so keep digging into those. I love having them. So I'm going to kind of focus first on multi-threading, just because I think it's a much easier thing to work with, and I think the mental overhead that you have to learn is a little easier. So multi-threading is one of these ways that you can use to alleviate this annoyance of having to wait for sequential expressions to complete. You can have one thread go do task A and then one thread go do task B, and it's perfectly fine. They'll reconvene when they're both done, and you can use up all of the parallel capacity of your computer. Okay, I use this example, but I now hate my example because we've talked a lot about like the difference between threading and processing, and I'm just going to ignore it for now. I'll talk a lot more about multiprocessing, and you'll kind of feel a little bit more of a difference. But multiprocessing, I think probably our conclusion from the break is that like multiprocessing is just kind of like it becomes more useful and different in a big cluster computing environment. Okay, multi-threading is kind of a make one process have more resources available to it kind of deal. And on my computer, like just a single machine, multi-threading and multiprocessing don't end up being particularly different, except for some minor differences in performance and how you write the code. Okay. So you have to start Julia with threads. You assign it a thread pool at the beginning here. I'm learning from the CS people in the audience. And so you have to assign the threads ahead of time. If you do not start Julia with threads, you cannot add them without a lot of work. I don't even know if you can add them during runtime, but I don't think it's a good idea. So you have 2 ways of doing this, depending on how you're using Julia. So the first one, if you're in the command line, you type Julia and then -- threads is equal to number of threads, right? So this is just a common command line argument. And you can give it n threads. If you know the number of threads you want to add in, so if you know the number of cores or if you're on an Intel processor that's hyper-threaded, so you can just do cores times 2. You can type that in, or you can do Julia threads equals auto, and it will use your system to infer how many threads it should spin up. So this is kind of my preferred way. If you're, just whatever, like I don't want to like, sometimes I provision fewer threads than I need, than auto would give me. So auto will give me 16, which is the maximum number that is like a good idea to do on my machine. But sometimes I'm like, I don't really want to take up all the resources on my machine, so maybe I'll just do 4 threads. That's also perfectly acceptable.
Yeah, definitely don't do auto on the ends because you don't want to grab all of the resources.
Yeah, that's a good idea. Yeah, somebody would get annoyed at you, and it's probably Natalia. So please don't do that. Just do this one. So typically on the ends, I just do, threads equals 12 or threads equals 6, depending on how like complicated my task is. If you're in VS Code and you use the REPL, so you do like control enter or shift enter to run lines of code, you need to actually go to the Julia extension settings, search for threads, and then enter a number. So 4 is like kind of safe if you know how to do that. I'll show you where that is. So if you go to extensions, and then you go to the Julia extension, hit the little gear, extension settings, and I can type in threads up here, and then I can type the number of threads I want to use when I spool anything up. So I can type 8 here. And now anytime I start the Julia REPL, it'll use 8 threads. Okay. So those are kind of the 2 ways to do this, right? So you'll want to have some kind of threaded Julia process running to follow along.
Quick question about that. Under the hood, is it using the command line argument? Like when I type Julia in the...
Yeah. Oh, you mean in the REPL?
Yeah.
Or in the VS Code REPL?
Like when I start Julia.
I guess I'm not sure what you mean by the command line argument. Like,
so you typed Julia to start it in your shell, right?
Yeah. So here, when I do this, I do Julia project threads equals 8.
Yep.
And so I can check this with Julia and threads. It'll give me 8. So when Julia starts, it checks this. There's also an environment variable if that's your kind of thing. So Julia num threads equals 8. So if you're like in
what did changing the settings do in the extension?
Oh, in the extension. So if I run control enter, VS Code has its own REPL to evaluate Julia code. And so you have to like specify a way of passing that to the VS Code thing. So let's see if it actually did it. Yeah. Okay. So it did 8. So that's what happens. If you actually just use the terminal in here, you can just, actually use the command line arguments. And this is my preference. I don't prefer the VS Code REPL. I just kind of use the default one. Okay. Alrighty. If you are in Jupyter, you'll have to make a new kernel. Is anyone actually using Jupyter? Following along in Jupyter?
I am.
Okay. So one way to do this is you can run that in your REPL. And that should give you, you can specify an environment variable that's local to your kernel. It's a little annoying. Okay. So once we have multiple threads, we can start doing cool stuff. Like, yeah, we can do all kinds of stuff. So I'm going to start with the lower level construct called spawn. And spawn here is a macro that basically means take an expression, some kind of thing you want to do, and give it to a thread and tell the thread to go run with it. So like this is equivalent to like if you have friends helping you move, you say, hey, Wanda, come over here. Wanda, I want you to take this box to the truck. And then you go do other stuff. You can go packing, and then Wanda will pack the truck for you. And eventually Wanda will come back to you if you want to see Wanda again. You could just ignore Wanda if you wanted to, but probably a bad idea. Because Wanda's cool. She helps you move. Like, don't be a dick. So, so spawn is non-blocking. This is important. I'm going to talk a lot about what is blocking code and what is non-blocking code. Blocking code basically means, do I have to stop and wait for the thing to finish? Okay, and I'll give you an example of what this looks like. If it is non-blocking, it'll just run right past that line of code. It'll do something very basic and your thread will go off and you'll have to check in later to make sure that it has actually completed its computation. Okay, so here what I have is just some code. I've created a B function and I've used this kind of very non-standard syntax so you can kind of get a taste of this begin syntax. So begin just is like a block of code that just you can put multiple expressions in it. And so what happens when I call this B function is it'll wait for 5 seconds. That's a long time. I don't want my main thread to be waiting for 5 seconds, so I'm going to ignore this. You know, this is here. This can proxy for something that's really hard, like solving an optimization problem or whatever. And then it's just going to return the dot product of, you know, 2 random 1000 by 1000 matrices. Okay. All right. And then I'm going to create a variable called task. And inside of it, I'm going to put the result of threads.spawn B. So what this says is, hey thread, one of the threads I have available, will you please go do B? And what gets put inside of task is a little different than what you might be used to seeing. It is called a future. And a future is like when you give a thread a task, hey thread, will you please go run B for me? You also give it a box and you say, I would like you to put the result of B inside of a box. And I'll be able to look inside of that box later on to see if it's there. And so that's called a future. And so what I'm going to do here is I'm going to run this code. And you'll see that it prints out waiting, right? So what's happened is because this line is non-blocking, we're going to spawn the thread. We're going to wait. And then we're going to fetch the task. So fetch is a blocking line of code. So we will stop here and wait until this thread is done. And it will return whatever is inside of the future box. So when Wanda finally puts the box in the truck, she'll be like, hey, Cameron, I'm done. And I'll be like, okay, I can move on and we can, you know, assign the next task. Okay, so does it make sense what's happened here?
So do you have to have the fetch?
You don't have to have the fetch if you don't want to. There's other stuff you can do. So for example, if you call wait task, this doesn't actually return the value in the box. It's just a blocking, you just wait for the future to be filled, for the thread to finish.
So I'm thinking, I guess what I'm trying to get at is like thread safety and like racing conditions, right? When your threads are doing computations and one of them didn't finish and you end up with incorrect values, right? So for that reason, we like wait for all of the threads to finish.
Yeah, so I'll give you an example of this in a second. But if you're waiting for 2 threads to finish, you would call wait or fetch on both. And so if you call fetch on both, they will both be blocking operations. And then you have to wait for both threads to complete. And then you can kind of, if that is the type of race condition you're worried about, that's a good way of stopping that. The thing that you're talking about that's an issue is if I do task.result. So task.result is, if you're used to the sum construct, sum or none, right? It is going to be a none if the task is not done. So if I do this, so if I print out task.result right here, you'll see it is nothing because it has not actually, the other thread hasn't gotten to this point yet. So if the thread isn't done, there's going to be nothing in the result. So you can do this thread.task.result, but it's stupid because you can run into some kind of like intermediate calculation issues. I don't know if that answered your question at all. Okay, we'll see. All right. Okay, so I'm going to go through this expensive code example I had before and make it a threaded construct. And this, I hope this will like get to a little bit of Natalia's thinking about the race condition problem. So I have this expensive function. Nothing's changed here. I have a serial version of the Go code. This was the original version, right? So this is do A, wait for A to finish, then do B, and then add them together. And then I have the threaded version of this where I spawn a thread to handle expensive, and then I spawn another thread to handle expensive. And these will be A and B. A and B now are futures. They are not matrices yet. The results of fetch A and fetch B, those are matrices. So when I call this, we're going to block on this line until A and B are computed. So when the task I've assigned to do this and the task I've assigned to do this are both completed, then Go threads will return. Okay, so this runs this code here. And this is where I want to show you that threading does not make things fast, right? This is like a thing that people have in their head where like sometimes you can just like add threads to stuff and it'll go faster. That's nonsense, right? Sometimes like having a lot of threads and like just like flippantly parallelizing stuff is a really bad idea. And so I hope this is like kind of helps you internalize that threads are just not like free speed. Okay. So I'm going to benchmark these two lines here so we can see what they look like. Let's see them roll in. The first one here is going to be the serial version of this. And then the second one is going to be the threaded version of this. All right, so the first one here is in. So this takes, a median time of 239 milliseconds, which is pretty slow, especially, in general. It has a lot of allocations as well. And I don't know, I'll probably talk about this in the performance programming bit, but you kind of want to keep your allocations down. Now we're looking at the threaded version of this. 239 millisecond median time, 269 millisecond median time. Wait, so the threaded version is actually slower. And the reason for this is that these operations are not expensive enough. They're too cheap to do. And so when you, this is equivalent if you think about Wanda, our friend who's helping us move. If I ask Wanda to move a piece of tape 3 inches closer to me, and she's in the other room, that's a huge waste of everyone's time. Like, I don't want to like have to like give Wanda, like asking Wanda to come over and move the tape is like a lot of work for both her and I. I could just get up and grab the tape. It's 3 inches away. And so when you have tasks for threads or processes that are kind of small, it's just not, it just doesn't give you that free speed that you would expect. Okay. So I just want to kind of like make sure that you guys see that it's not always the best idea to just multi-thread stuff. Do people understand what's happening here, or at least get the point I'm trying to impress?
Is there a way to change number of threads inside a notebook without installing the kernel? Can I like modify the environment variable?
I don't think so. I think it has to be the ahead of time.
Okay, can you print out the number of your threads in the notebook cell?
Oh, that's why I'm running the wrong kernel. Oh my God, I did the thing. Yep. Oh my God. Yep. Crap, that's really annoying. Thank you for checking that.
I did the same thing because I didn't know how to, even though I installed multi-threaded kernel, it still shows us one thread in the notebook. Maybe you just do it in the.
Yeah, I did this on my laptop where I have the kernel, and then I did not do it on my desktop when I converted over. Okay. Well, let me redo that. Okie dokie. Ha 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 ha. All right. Cameron's been made a fool for the better. Thank you, Natalia. Okie dokie. Let's see if I actually have the threads I want. Oh, I didn't pick the kernel. Oh, did I do auto? Oh God. Yeah, this is like a whole thing now. Well, this is going to be annoying.
I'm so sorry.
No, this actually needed to happen. Expected string or bytes like object. Doop, doop, doop. Yeah, living it up. Live debugging. Is this what you guys came for? Are you not entertained? Okie dokie. Let's hope that actually worked. This is very annoying. Alrighty. I am super sorry about this. Oh my God. Well, this might be a good time to take a brief pause while I figure this out, because otherwise this is going to be very, very boring. Oh, there it is. All right, cool. Ha 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 ha. In the nick of time. Alrighty. And let me rerun this and rerun that. Oh my God. And now it's outside of the project. Wow. Okay. Yeah. Why don't we take like a 5-minute break while I figure this out? So, all right. Hello, everyone. Welcome back. So basically what happened is the Jupyter is nonsense and I don't like it. So basically what I'm going to be doing is I'm basically going to be copying the code examples over and showing you how I'm going to run them in a VS Code environment. So I'll show you what that looks like. All right. Oops, I'm already in it. All right, so here I have my Julia session here on the left, and over here I'm going to have the code here. So this will basically be, I'll add these benchmark code here, and the benchmark code for this one. Alrighty. Okay, so I'm just going to do this include thing. The include says, please go load this file and execute all the expressions in turn. I'm also going to use this code, this syntax intermittently. So because I'm working now in like a, I'm working with actual like scripts now, I'm going to be using what's called the pipe symbol. You may know this from R. The R version of this is the percent greater than, or yeah, percent greater than percent sign. In Julia, it is pipe symbol greater than. And the display function just says, please print it out to the REPL. Okay. Oh, that is not what I wanted. Actually, I have to wrap this around. Okay. I apologize while I get my bearings here for a second. Okay. So it's going to benchmark these, and hopefully we'll see some kind of speed increase because now I've had plenty of time to compile all of this code. Okay. But while that's running, I basically wanted to talk about the spawn function that we're using to ask a thread to go do something. So spawn isn't super common. Because generally when you're working with like a lot of data, you kind of want to like ask a bunch of threads to go do like the same thing. At spawn is kind of like a, you know, hey, thread A, I want you to go like handle, you know, input output, or spawn onto thread B, I would like you to go like handle like client requests, things like that. That's like more of like a web server, you know, like more of a systems programming type paradigm. So at spawn doesn't tend to get used a lot in like kind of academic style Julia code. I'll talk about how to do that in just a second. But I want to show you kind of our results here. Let me make that bigger. Okay, so basically what we have here is that now the multi-threaded version is slightly faster. Not a whole lot faster. It's not half as, it's not, you know, half the speed. You know, if you have 2 extra threads that you apply to one task, it doesn't just cut your time in half, right? That's, I think, what people would normally think, and that's not what happens at all. I'll show you a little plot later on about how it scales with the size of your data and how complicated the tasks are. But in general, this example kind of demonstrates that threading just does not make everything better. But it can. So this is an example here that I wanted to demonstrate, and finally I demonstrated it correctly. Okay, so any questions on what I've done here? And I understand the last like 5 to 10 minutes were super confusing and weird.
Sorry, just to clarify about the spawn, all that does is like thread go, like put this process in the thread.
Yeah, put this function, take this expression,
Yeah.
give it to the thread. Hey thread, please execute this expression.
Okay.
Exactly. Okay.
Sorry, and then a different bad question.
No such thing as bad questions.
How would this look if we were trying to put these into sub processes? Do you have any reason to think they'd be faster or slower?
They're not going into separate processes. They're staying within this process. I'm not sure what you like. How? Why are we?
The way that you wrote it is in the multi-threading way. Could you have done this with multiprocessing?
Yes, yes, you can. The difference is basically, I'll give you a preview of what the code looks like. That's the difference.
Okay.
And my guess, threads are faster.
Yes.
Memory is localized.
Can we check?
Could we check whether it's faster? Not without a little bit of work. It'll take there's some setup that involved in getting the processes to work, but we can revisit this during a break and we can we can figure it out.
Sounds good. Thanks.
Okay, so I wanted to run this code as well, so you can see what it looks like. What is this one going to call? So I wanted to show you something that's very important about multi-threading that may not occur to you if you haven't spent a lot of time in it. So I've written this function called thread test, and I'm going to use this new construct called threads.atThreads. And if you put this macro in front of a for loop, what it will do is say, it'll look at your thread pool. So I believe I have 8 threads, and it will delegate to each of those threads some value of I that's in this collection. So we'll assign, you know, maybe thread 1 will get I equals 1 and I equals 2. And there's kind of just this like, I don't actually know what the scheduler version is. In like some other languages, you can like configure like whether you want like a round robin style allocation. In general, you don't get like a whole lot of control about like your thread allocation method, but in practice, Julia's default is pretty good. Then I'm going to create a variable called thread ID that is just going to use this thread ID function. This just says, what is the ID number assigned to this thread? So if I have 8 threads, I have IDs 1 through 8. And then what I'm going to do is ask each thread to print thread ID and then the ID, and then the value of I that it received. Okay. So I'm going to run a thread test. Actually, what is my working directory? Okay. Where is this saved? Ah, live. That's why. Okay. So look at this and notice something weird. First of all, it's out of order, right? It is not 1, 2, 3, 4, 5, 6. It is 6 and then 5 and then 2 and then 4 and then 3 and then 1. 6, 5, 2, 4, 3, 1. Okay, so if you were asking the thread pool to complete all of these tasks to do it in order, you're very wrong. So this is going to be very, very important later on. All of these threads are going to come across this loop, and they will be at different points in this loop at different points in time. That's super important. And this is going to be a lot of the reason for why it is that we're going to have to do all of the things we're going to have to do later. Okay. So anytime you put this threads macro before a for loop of any kind, it's going to be out of order, out of the order that you think it should have been in. Okay. And I think importantly, it's non-deterministic. So if I run this a bunch of times, depending on CPU resources, depending on all kinds of things, it will always be different. Okay, so be careful of this. It's not, it's meant to do a lot of things that don't depend on order. So if you need this loop to solve for I equals 2 first, you probably shouldn't be using multi-threading here, or you can within the context of the loop, but the loop itself, you don't really want the things in there to depend on one another. Okay. Does this make sense? What's happening here and why this is possibly a concern? Okay. Cool. So the order of these threads is not deterministic. Threads show up differently when you rerun the code, and they're assigned to different parts of whatever the looping variable is. Okay, so that's important. So when you're doing this like threads.@threads macro, remember that the best way to think about that is assigning a bundle of tasks. Like you're basically just throwing a bunch of tasks to your friends, and your friends are going to get to whichever ones they're going to get to. You don't necessarily get to control which one goes to thread 1, whether thread 1 completes I equals 1 before I equals 2, so on and so forth. Okay. So I'm going to give you like a fast example of threading. This is kind of a dumb example, but I want to show you like how to do it kind of well. Okay, so here I've written this function called serial sum. All it does is create this R variable that sets equal to 0. It's going to go through every value in the array XS that we give it, and it's going to add I to whatever R is, and then it will return R. Okay, so this is kind of a like classic lazy example of a sum function. Then I've written a thread sum version. And thread sum actually creates a vector of zeros. So basically what we're going to do, it's going to be the size of the threads. So if I have 4 threads, R will be a bunch of zeros of length 4. So there will be 4 total zeros. Then I'm going to go through I'm going to assign every value in XS to a thread, and each thread will go into the location in R of the thread's identifier. So thread 1 will only work in R1. It'll keep adding to R1, so on every element of I that it observes. Okay. So then I'm going to create some values here, which are just a bunch of random numbers. Oh, does anybody have a question about this one? Okay. Alrighty. And then I'm going to benchmark the thread sum. So I'm going to benchmark these two so we can see what they look like. And this one I'm actually kind of amazed with, like how kind of well it worked, because this is a very easy to parallelize problem. Oh, and the last part to note here is I add up all of the workspaces at the end. So each thread has its own workspace where it's accumulating values, and then it's just going to add them together at the end, all the different workspaces. Oh, that is not what I expected. Oh, that's interesting. Okay, there it is. Yeah. Okay, so here's the part where it's, oh man, all right. So the previous version when I ran this was actually slower because it was single threaded on the core I had. Okay, so that means this code is actually really efficient. Single threaded, but it's absolutely terrible if you multi-thread, right? So this is two or three times the cost that you have here. So this is, I've switched examples. So this example that I wrote here is actually faster when you use threading, but not by much. This one's about, what is that, 2 or 3 times as slow, just because I have to parallelize across. It's very annoying. Okay.
Sorry, Cameron, I didn't understand why it's slower. What is different here? Can you explain it a little bit more slowly?
Yes, so there's a couple parts that's different. Here I have a single variable that I'm accumulating to. I go through each value of XS in turn. So the first value, then the second value, then the third value, and then I add it to R each time. In here, there's a lot more complicated stuff happening. So first, R is a vector of zeros. And then each thread goes into some particular vector and just like starts adding stuff to its little workspace. So each thread basically has its own value of R. And then at the end of it, I'm going to take each of those 4, if you have 4 threads, there's 4 workspaces, 4 versions of R with different that are sums of different partitions of XS. And then you can just kind of smush them together.
I see. So basically, rather than just keeping the same number in memory, you're allocating space, changing things in different spaces, and then combining, and that takes time.
Yeah. So let's try an example here to see what happens when I have a 10K by a 10K matrix. In principle, it should be a little bit more costly. Actually, here I'm going to change this to do time. So then I don't have to do a full benchmark. So actually here is a case where threading becomes much better. Right, so the serial run for this big 10K by 10K matrix, the serial sum is 0.219 seconds. For the threaded version, it's 0.07. So if I have small data here, so like let's say I'm doing this with like 100 values, it's super easy to add 100 values together. Threading is way worse. It's orders of magnitude slower. But as your data gets really, 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 really huge, it becomes much more advantageous to have, if I have 4 threads, I'm partitioning a quarter of the array for one thread, and then I'm partitioning a quarter for another thread and a quarter for another thread. And each of those threads can work independently, and so you benefit a lot when your data is really big. Okay, that was the point I was trying to make with this one. Okay, do people understand what's changed there? Where I've kind of done this partitioning of a ton of data, and it makes it much faster. So big data, threading is better. Small data, serial is better. And part of this is just because it's costly to ask threads to do stuff, and we have to like allocate this vector here and do lots of little tiny array operations that add up for very small data.
Sorry, can I ask a really silly?
Sure.
Where are you setting how is the number of things the same? Where are you actually splitting your values into number of threads?
So that's this part right here. So the threads.atThreads macro basically looks at the array and it looks at what's in XS and it handles the delegation amongst them all. So and it'll handle them kind of dynamically. So if one thread, like if one value of XS is really hard to do the loop for, the other threads will take up the slack. So in principle, one thread could be assigned to just like the one really hard to compute value in there. And because it doesn't keep coming back to the scheduler, it'll go to the other ones. And those ones will take up a lot more of the slack. So this will handle dynamically how you allocate.
So in principle, anytime you have any sort of simple for loop where you don't care about the dependency between iterations, you could just pop this in and it'll like optimize it automatically.
Yes, in principle, but there's with some caveats, and I'm going to get to that in a second. Okay,
Can
So
I
I'm,
ask unrelated question? If you go back
yes,
to
of
your
course.
code. So I see a lot of functions, and usually in Python, I like to document them. So I guess my question is about like,
Style.
is there, yeah, so you know, in Python how we do like triple quotes, and then that's converted into docs that I can search or like make a website or whatever. Is there like a standard way to document, Julia?
Yeah. So this
Yeah.
is the common way. So
Okay.
if you do triple quotes just above the function, actually here, let me
Above the function?
yeah, do
definition?
it
Okay.
do it directly above the function, and then I should be able to do thread sum. So
And
if I
you
do
can
one,
source that. Okay, gotcha.
yeah, so it'll automatically assign that as part of the into the doc string. Good question. Good style question that I've been flippantly ignoring. But yeah, when you're writing like lots of big code, that's like a really good idea. Like it's kind of necessary. If you start contributing code open source, you know, document your functions so that people know what they do and why it is that you're doing it. Okay. Cool. So I want to talk now about race conditions. So remember that thing I showed you where we were running across this array and it was being assigned to different threads, and they were being completed in different order. Well, that's kind of a huge problem sometimes, especially when different threads need to modify the same thing. So I'm going to take this code here. And I'm going to run this here. So let me move this up to the top because I hate having imports mid script. It's bad form. So basically what this code does is I'm going to create an empty array called XS. And then I'm going to multi-thread across 1 to 1000. So I is going to take the value of 1 to 1000. It'll be assigned to kind of random threads, and they'll go along. And then this push function here basically says take I and stick it on the end of XS. Okay. So at the end of this, XS should have 1 to 1000 in it, and they'll be in a random order, or at least that would be our best guess. Okay. So note this number here that I've printed out, 556. That's the output of this line here, which is print line length of XS. Wait a minute. There should be exactly 1000 numbers in there, not 556. If I run it again, 575. What the hell's happening here? Now it's 982. It almost got there. This one, 708, doing pretty good. All right. Oh, here, bad. That's right. I had like this right here. This is a compiler nightmare, right? So I just seg faulted here. Like this is real bad. So you can't just modify one thing that all the threads talk to. And the reason for this is, in these cases here, where I was just getting a different number, no segmentation fault, what's happening is each thread is at a very different point of their life cycle. So to expand on what's happening in this race condition, there's a couple of steps that happen when we call push. So first, it has to actually see what's in XS. Then it has to take I and stick it on XS and then update XS globally, okay? In between 1 and 2, another thread can come along and complete 2, their own version of 2. They've already appended I to their version of XS. And when they update it globally, XS is now different than what one other thread saw from XS. And so when they write it back, when the current thread, not observing the other thread having updated XS, comes along, they're just going to blow past whatever the other thread wrote and put in their own version of XS, right? So these threads can constantly step over each other by like writing back to it things that they did where they don't observe the other threads because the other threads didn't get to like tell that thread what was in the array before they got there. Okay, so this is like one form of a race condition. There's like a million others that are just like, you know, it's a very, I think of it as like kind of like a big cloud of problems that happen when threads aren't necessarily aware of what's happening. They're trying to modify shared memory. They're trying to do all of this stuff. They're acting independently, and they're not, you know, the threads don't talk to each other. So race conditions are going to happen. And most importantly, you'll note I had to run this how many times? 1, 2, 3, 4, 5 times before I actually got an error, like a noticeable error, and a big error at that. Like this is not like a, you know, segmentation faults are bad. If you get a segmentation fault, you did something bad. It even killed my process, and it did a core dump, right? That's horrible. You don't want that to happen. Importantly, it failed silently 4 times. So you have to, like, anytime you turn on threading, you have to be super careful, because it can fail. You can run into a race condition by accident if you're not paying attention, and all of your numbers will be wrong because the threads are stepping on each other's feet. Okay, so I'll give you tools to fix this too, but just keep that in mind, that if you see anything with an exclamation point, be careful, because it mutates one thing. Okay, by convention, the exclamation point at the end of a function means mutate this thing. Okay. If threaded operations depend on results from other threads, that's an issue as well. Go ahead.
Is there any benefit to using immutable types when dealing with threads? Is there any sort of like standard practice to sort of make sure that you can't do this?
Well, the immutable types make it more obvious, right? But it depends on how you want to get them out, right? So a lot of cases when this occurs is when you're constructing, like, so let's say I had like something called like a equals 1, b equals 2, b equals I. Let's do that, right? So if I'm creating this immutable structure in here, I have to get it out somehow. And the way that I get it out is by pushing it onto this kind of mutable state, or by like pre-allocating this vector and sticking it in there. So like you can have immutability to some extent, but you have to have some way of getting it out of the thread. And there's other ways to handle that. I'll point to some of those a little later.
Yeah, is there a way to write in parallel to like a data frame or a CSV file? Because I know it's very difficult in Python.
Yeah, not without a lock. What I do for that is I just throw a lock on it. And we'll talk about that in a second. But we're at the top of the hour. I think we should like stop to do a break, and we can continue chatting during this thing, but we can pause the recording for now, I think. Back up at the top. Okay, welcome back, everyone. So when we left off, we were going through basically this race condition thing, where when I run this code, it does not deterministically give me the same amount. It does not set all 1,000 numbers inside of this array, because all these threads are competing with one another to assign values to global memory. Okay, so I went through the race condition, and I gave you some things of caution, right? So watch out for when threads are modifying things outside of the threading loop. So note, for example, XS is outside of the threading loop. If I was doing something like this, where XS is thread local, that means that inside of this loop, each thread has a copy of XS. You can do whatever you want to XS. That's fine, because each thread has its own version of that. The second you put it outside of here, each thread is if they're all trying to modify it, that's an issue. Okay, so watch out for things that have exclamation points, the functions that have exclamation points that modify things on the outside. This also goes for really basic array operations, such as like XS1 plus equals I, right? If you did this, every thread would be trying to increment the first value of XS by 1, by I, whatever it is. And that would also be a problem, because they're all trying to talk to the same location in memory, right? So these are race conditions. Also, don't do like input-output operations multi-threaded, kind of dumbly, right? So if you're like have two threads that are trying to have each have a data frame or a CSV, something they want to write into like a comma separated value file, and you try to write them together at the same time, they will overwrite each other, and it will be nonsense, right? Your file will be nonsense, depending on how it writes. Either it will be one thread's result only, or it will be a garbled nonsense if they do stream flushing. That's kind of like a whole bad idea.
Do you ever use something like HDF5 that is able to handle parallel streams?
Yeah, HDF5 is like, there's actually a really good HDF5 package that supports it. That's really good in case you want to use like actually really
that's
good
one way in Python where I could write in parallel is using H5py wrapper around HDF5.
Yeah.
So okay.
So if that's something you want to do, you can use hdf5.jl, which is a very good package for working with HDF5. HDF5 is like a high performance kind of data format that's like, not CSV, and is a little more hierarchical and kind of a little easier to work with. So if that's the kind of thing you're working with, like a lot of like multi-threaded input output, HDF5. And even if you are working with CSVs, I can give you a little trick to do that, to work with that, and so if you so choose. So the thing that solves this, at least to an extent, is what is called a lock. And a lock is a way of putting a little gate around some code that only allows a single thread inside of that block at a time. So locks are a way of making sure that one thread can go into this block, do whatever it needs to, and then when the next thread comes along, it's not going to step on the toes of the other thread. Okay, so you can think of it as a door that only lets one thread in. So if there's a thread inside of the room, you cannot go in. Once that thread leaves, then a new person is allowed in. So locking things basically gives you a guarantee that nothing inside of the lock can be influenced by other threads, right? Well, sort of, within bounds. If you write crappy code, I can't guarantee anything. Like you do all this like stupid pointer reference stuff if you wanted to, but that's a bad idea. So I want to use a lock to this previous code. Remember, we had this thing here where we were appending values. Each thread was trying to stick values on the end of this array, and it gave us 160 out of the 1,000 we expected to see. And so what I'm doing here is I'm creating a lock, and this is called a reentrant lock. A reentrant lock is like a pretty performant lock. This is the one that we're kind of recommended to use in Julia for currently. There's also spin lock, if that's something you prefer. Spin lock is a not as good an idea because it just like each thread, they're all pooled up waiting at the door, and they just keep knocking until they can be let in. Whereas the reentrant lock is a little more of a revolving door. It's like, there's less like CPUs just idling at the gate waiting. Okay, so I've created a lock called XS lock. You'll note that the lock is declared outside of the thread loop, which means all threads can see the lock. That's really important. You want all of the locks to have, if you did this where you put the lock inside of the thread, that means nothing, right? This lock is not shared, it's thread independent. So each thread has its own version of the lock. So if it just tries to lock its own lock, it's the only thread that will lock its own lock. So if you put it outside here, that's a wise idea, okay? Then there's this syntax here called lock do. So lock do basically says, try and take control of XS lock. So if no other thread has control of XS lock, then the thread who gets there first will take it. They'll step into this block and lock all the other threads out. Then what they're going to do is add their value of I to XS, and then the block is done, so they're going to exit the lock. Once they exit, there will be other threads who are queued up at the beginning of the lock who will step in and do whatever they need to inside of the block. Okay, this is syntactic sugar. Syntactic sugar means shorthand for lock XS lock. I believe it's unlock XS lock. and then you would do stuff here. This is the common paradigm. This do syntax basically says unlock it when this block is done. I don't prefer to do this stuff because sometimes you can like forget to write XS like to unlock it. And if you never unlock the lock, then all the threads will just stop. There will be just one thread, and we'll always have the lock, and none of the other threads can do anything. Okay, and then we even just like loop around, come back to the XS lock, and yeah. So it's just like, I prefer this syntax to have a separate block, but you can do it the other way. This is kind of the older school way, I believe.
Quick question.
Yes.
About this. I've seen a lot of people when they do this do wrap the unlock in like a try finally, just because if there's like an error in the code that so you like lock before the try.
Oh, that's right. Yeah.
Or I think so. Yeah, I think you lock before the try, then you do the try stuff, and then you finally, and then unlock in there. And
yeah, I actually would think of these as equivalent. So what happens here is that if I believe in the do block, if you get an exception, if this thread gets an exception, it will unlock. So like that is kind of similar to this finally construct here. And then it's just less verbose. And I don't like people seeing that I've written try catch finally, just because it like makes me feel like other people are judging my code, which is not true, but I don't know. I also like the like story about this, right? This block here is a room that you can one thread can enter at a time, and they will all wait right here until they can file through this room single file. So that's why I like the lock do syntax. Okay, and we'll note that I can run this as many times as I want, and it will always have 1,000 values inside of the array. There is no more race condition here because the threads are always waiting. Every time one exits, they will enter with their value of I and stick it on the array. Okay, questions about this? What's happening here? Okay, so I have some heuristics about when it is that you should put a lock on stuff. And there's like a lot of resources out there about like when to program well with locks and what kind of good heuristics you should use and other stuff. These are the ones I've found most useful. So use locks when reading, writing, or modifying variables that are shared between threads. XS is an example of one such variable, and push is a function that modifies XS. So anytime you have that, you should probably put a lock anytime a thread would modify a globally shared variable, or something that is accessible to the threads. Don't lock too much. Like try and if you can, try to make it such that getting to the lock is kind of a big deal for every thread. Like, so every thread should do a ton of work, and then they show up to the lock, and then they just do this. They're in and out real quick. They just like pop something on an array and then they leave, right? That's kind of what you want it to do. You don't want to spend a lot of time in locks, because that every time you have a bunch of locks, you have locks like multiple locks within some kind of thread call, something like that. You have to, all the threads are going to stop and wait. And like if you have two different locks, you have a single file as they go through the first lock to get to the second lock. So there's like a, you don't want to put a bunch of roadblocks in the way of your multi-threaded code. You just want to kind of do one lock that's like a big deal, where you just kind of pop something into an array and try and make it as fast as possible. You want to spend almost no time inside of a lock. Which leads me to the third point here, which is do all the computation you can outside of your lock. You want your thread to be ready to go when it has a turn to get to this array XS. It wants to have done all the math you possibly can before you actually just do this changing step. Don't do the math inside of the lock. That's a waste of time, right? You can do the math outside of the lock, and eventually when you get to the array, you can deliver the result to the rest of the world. You recall I did this like array threads.threadid trick. I think you know, some people think that this is okay. Other people get really nervous about this. Actually don't know what the answer is. I believe it's fine because it's always a pointer to the same location, and each thread only modifies the same location. This is fine
as long as you're not using a data structure where you're like dynamically resizing.
Yeah, so no dictionaries. Don't use this with dictionaries. Use it with arrays. You know, like if you have like a very simple base array, it's fine to do this, because it's just, you know, each location is just a pointer to another spot in memory. So if you're using like dictionaries or ordered collection, like any of that stuff, it's just kind of like nonsense. So just kind of, if this is like a bunch of zeros or a bunch of numbers, just like in an array, this is fine. But don't get too complicated outside of this. You know, if you start modifying dictionaries, put a lock on it. Because anytime you add something to a dictionary, a new key, for example, to a dictionary, you have to rebuild the hash table. Okay. Questions about the heuristics, or maybe what they look like? Okay, cool. So let's actually give you guys, let's get your guys' hands dirty a little bit, and let's write some code. So basically, I'm gonna assign you this kind of really simple Monte Carlo project here. So we'll spend we'll spend like 10-15 minutes as needed on this, and until we kind of figure stuff out, and we can work through some questions people have as we're building some stuff, and this should be nice and simple. But let's say we have like some mass of agents, and they have this utility function. Each of them has their own utility function, which is just UI, and it's a function of some vector of stochastic goods X. And it's just going to be exponential power utility here. So 1 minus the exponential of their negative risk aversion. So each person has their own risk aversion times whatever the goods are times their preferences, beta. Okay, so let's imagine that all of these are stochastic, right? That, you know, we were drawing individual people from this like population, and they all had their own betas, which followed this normal distribution. They all had their own gammas, which was exponential. And then we had this, you know, the distribution of goods here is mean 1 with a variance of 0.25, no cross correlation. So super simple. And let's say that my question is like, what's the distribution of these utilities, right? Which is also kind of like a silly question. Like, I don't know, maybe you don't care that much about the distribution of utilities because, like, you know, they're ordinal. Like, it's just kind of a weird thing to do. But it's just kind of a good example to like think about generating a bunch of numbers and seeing and doing some math, and then generating a result value and sticking those things together. Okay, so I'm going to give you guys some starter code here. Pull up the chat. Okay, so what I want everyone to do is write a function that simulates 100,000 draws of X, beta, and gamma I with multi-threading. And I'm just going to assume you can just fix n, which is the size of beta and X, to 10. And then I just want you to calculate the utility for each of those combinations and store them in an array. So your function will, you know, take all of those 100,000 utility draws and return them to the user. Okay. If you're feeling like you can get through this pretty quickly, you know, you can take Unicode plots and plot a histogram of the utilities to take a look at like what the actual distribution is. You can add an outer loop to your simulation function to change n from 1, 10, 15, 20, 30, and 100, and stick that in an array in a matrix, a 6 by 100K. And there's a way to do this with and without a lock. And so if you did this one way, can you think of how you might do it the other way? So I kind of want to just see people tinker around with this, and I'll be around to answer questions as needed. And I'll pull up to chat too. I'll be monitoring the chat much more intensely right now, in case anybody wants to why isn't this working? Yeah, why don't we pause the recording for now? See how it is that thank you very much. So let's go through my answer. Okie dokie. Okay, so I'm gonna have a whole bunch of my code here on the left. So I'm just gonna import distributions and linear algebra. And then I'm gonna add Unicode plots just so I can see, like, Unicode plots is actually a really cool tool for just like doing plots in the terminal. So you don't have to like talk through like a whole bunch of graphic stuff, which can be kind of costly. And they tend to look pretty good. Then I'm going to print out the thread count. So how many threads it is that I'm working with, so we can avoid my problem from earlier where I was just working with one thread. I'm going to define my utility function. So my utility function is a function of x, the stochastic goods, gamma, the risk aversion, and beta, the preferences. And then I've just typed all that stuff in here, right? So this is just the math. I'll put a little bit of spacing there. That looks ugly. Okay. And then I have this function here that does a single draw. All this does is draw x, draws gamma, beta, and then it calculates u from the random values of x, gamma, and beta. So this is the code I pasted in there. So this is just, x, gamma, beta. Just copy that right into this function. And then all it does is return the value of u. Right, so conditional on observing this distribution of goods, or this realization of goods, this realization of risk aversion, and this realization of preferences, utility is this, and I return that. Okay. Then I'm going to show you the serial version of this code. So as I mentioned, I always write the serial version first because it's the easiest to write, and then you can just add the parallel components as needed. So here, all I'm going to do is take n, which is how big you want the vector to be, the vector of goods and the vector of betas. Then how many stochastic draws I want to do. So how many simulations do I want to run? So in this case, I'm going to pre-allocate a result vector. So I'm just going to, if I'm going to do 100,000 draws, I'm going to make a vector of length 100,000. It's just going to have a bunch of zeros in it. And this will be an array of float 64. If you care about the types, which you should. And then for each draw, I'm just going to go through, I equals 1, I equals 2, so on and so forth into n draws. I'm going to calculate a draw. And then I'm going to take that draw and stick it right into the array. You could even shorten this a little bit because we're working in a serial setting, and just put that here. If you wanted to, that's perfectly fine. I don't need to have an intermediate draw variable. I can just dump it right into the array. Okay, and then at the end, it's just going to return draws. Okay, any questions about any of this code so far? Should be reasonably straightforward. Okay, now I'm going to do the multi-threaded version with a lock. So the big difference here is that now I've added a reentrant lock in the second line of this function. Note again that it's outside of our threading loop so that each thread can see it. Then I'm going to go through each, I'm going to do threads.add_threads across this loop. This is the same loop that I had before, just with threads.add_threads. But now I'm going to create a draw, and I'm going to do this outside of the lock because it's computation. I don't want to be doing a whole bunch of like math outside of or inside of a lock. And then each thread is going to wait at the lock. And then when it has its turn, it's going to put the draw in the vector that I pre-allocated corresponding to the simulation number. So in this case, if I was 15, it'll put the result, the U value that it got in 15, the 15th spot. Okay. And then at the end, it'll return draws. Any questions about this function?
Yeah, so I remember that like thread.threads doesn't go in order. But like, because we don't really care about like the order of these, right?
Yeah, yeah.
So like, is the lock really necessary? Like, what would happen again if you don't have it?
Actually, in this case, I don't think you need it. The reason you would need the lock here is if you were going to do, if draws instead was, if you pre-allocated a float, like if you did not know how many of these you were going to generate, if you did this
You're
kind of,
appending.
yeah, and you were appending, then you would need it. In this case, I don't think you need it. Yeah, actually, I'm not sure why I did it this way. And then I have a much more general unlocked version here, which is actually kind of a really terrible algorithm, I'm realizing, because what it does is it makes a big matrix with n draws, and it adds one column for each of the threads. And then each thread can just go into its own column. This is like kind of a really messy way to do this, because if you have 16 threads, then you have like 16x the memory allocation, which is horrible. So this is a bad algorithm. You should not do this. Just listen to Brian and do this. Yeah, actually, I think we could just I think we just do this. Yeah, let's see. Yeah, I think we can get away with just that. That would be the modification we could add here. But I guess my habit is more to, it's pretty rare that I work with this framework here where I have just like a bunch of zeros. That's like a really nice computational framework where everything just kind of tends to work really well. Like I tend to work with a lot of dictionaries and things like that. So I like to be in the habit of putting a lock on things when you don't actually need it. Okay. And I want to show people kind of what the performance looks like. Assuming there's no questions about the stuff that's up here. That was a good one, Brian. Thank you for noting that. Okay, so I'll run this. I'm going to have n equal to 10, and then I'm going to do 100,000 draws. And then I'm just going to call the simulate lock, simulate unlocked function. And then I'm just going to print this howdy line at the end, just because I like to have my code tell me something nice every once in a while. Okay, so here I'm looking at the performance here, and they're actually pretty close, right? So like the serial version is 0.07 seconds, and the two multi-threaded versions are 0.06 seconds apiece. And you will note that the stupid version I've made here has a lot more allocations, right? It's got 78 megabytes that it's allocating, which is a little costlier than this one here, where we just pre-allocate one vector and dump it straight in. Okay, so this might be a little concerning because like you're like, okay, well, I wrote all this damn code and like it was supposed to go fast. Cameron said it might go fast, and we want to kind of validate that that's something that's occurring. So I want to show you what happens when you increase n. So n is the size of this vector that we're doing inside of a single draw, right? So that's the size of x, it's the size of beta. So if you make n 100 or 1,000, then this is a much larger operation, right? Because you're multiplying and summing 1,000 numbers rather than, or 2,000 numbers rather than 10, 100 total. Okay. So this can make each individual thread's task much more significant. So let's say I made n to 10,000 and then I reran this code. Now the serial version sucks. It's 2 seconds versus a little over half a second for the good serial version. I'm actually just going to get rid of this one. Okay. All right. Anyone have any questions about what's happening here, right? The takeaway here is that like it's pretty easy, right? If you have something where you're just throwing into a pre-allocated vector, that's easy. Just do that. Just like put it in the vector, add threads.add threads, and you have multi-threaded code that was cheap and free. Don't even need to make this lock. Actually, make it a little speed up from that. Okay, so that's kind of nice and easy and fast. And we didn't have to work too hard to get to it. Okay, and if you're interested, we can plot out the histograms of the results to make sure that they're roughly consistent. And indeed they are. This is because my parameterization is a little wonky. So like if I make this if I make the risk aversion much smaller, or maybe even way bigger, I'll get something a little nicer. Okay, yeah. So both of these ways, construct statistically reasonable distributions of utility. All right, questions? All right, cool. I think we're at the top of the hour, so we'll take our 10-minute break here, and then we'll come back, and then I'll talk about multiprocessing. And I'll be around up again. All right, cool. So this will be our last little chunk here. I kind of just wanted to hammer home the fact that like multi-threading is really, really good when you have each thread do a lot of work. So some really good examples of this that you might run into in economics or like other social science type research is like simulation. So we just did an example of this in Monte Carlo, doing some kind of grid search. Grid search is a really good example because you can just give each thing a different grid point and have it calculate the result. Bootstrapping is like another, that's like a kind of statistical procedure that's really easy to parallelize. Okay, so these are often called embarrassingly parallel problems because they almost require almost no effort to parallelize.
Pleasingly parallel.
Pleasingly parallel. I like embarrassingly parallel. I like it to be an issue. So in a kind of a multi-threading context, you can get away with adding a lock if it's, even mildly complicated data structure, or no lock at all if we saw, as we saw before, and just putting threads.add_threads in front of a loop. Like that's really kind of sometimes all it takes. And if you want to make, a lot of the time that's good enough, but locks will help if you're like worried about race conditions and getting wrong answers. Okay, so I wanted to show you guys a brief example of how to like a more complicated case, and just kind of how I would do grid search in a multi-threaded way. And I'm actually pretty pleased with the performance of this. But basically what I'm going to do is I want to do grid search to calculate the maximum likelihood estimate of some data. So let's say I have like normally distributed data. I have a bunch of observations. And I want to find the mean and the variance of the maximum likelihood estimate of the mean and variance of my data. So I'm going to define this likelihood function here. All it does is I take some data, I take a guess of the mean of the data and the variance of the data. I construct a distribution. This is normal here is actually stored inside of distributions.jl. Then I define a function called t. All t does is it takes the log PDF of this distribution with respect to a data input. I'm going to call map reduce here. Map reduce is like map, but it doesn't actually give you a vector at the end. You supply it a reduction function so that you can add each value together as you go along. So you don't actually have to do this like array allocation thing when you use map reduce. So I'm going to take each element of all of my data points, call t on them to get the log PDF, and then add them up. So this gives me the joint conditional likelihood conditional on M and S. Okay, so that's nice and easy. And then I've written this grid generation function where it accepts a vector of data. So this is the things I'm trying to understand the mean and standard deviation of. Ranges to go through. So this would be like, what's the minimum possible range M and the maximum possible M, and how many steps do I want in between? So how fine and where is my grid? I'm going to define a empty array. You'll note that this is actually untyped, which is a bad idea. You don't want it to be untyped. I'm going to create a lock. And then I'm going to declare threads.add_threads for each value in M. So if my M range is 50 wide, I'll have 50 thread tasks. And then what I'm going to do is actually give each thread its own little buffer. So for each M, there's going to be an array of values that they can append to. And then it's going to go for each value in S. These are all my guesses about the variance. It's going to calculate the likelihood. It's going to create a named tuple. So I'm just going to take whatever the M value is, the S value, and the log probability here. And I'm going to assign that equal to V. And then I'm just going to push that onto the thread buffer. And you'll note I don't have to do a lock here at all because this, this thread buffer is local to this thread. So it can put whatever it wants on there. And then once it goes through all the S's, so let's say there's 50 values in S range, it'll go through all 50, it'll put them inside of a thread buffer. And I could even make this faster if I wanted to by pre-allocating this. I'm going to lock this VLOCK up here, and then I'm going to use append, which mushes two data frames or two vectors together. So I'm going to take my buffer and stick it on the master list at the very end. This is a good way to use locks here because I don't have to, I only have to do it once, and it's a pretty big operation, and I've done a lot of math to get there. Okay, and then at the end, I'm just going to call data frame on all of my vals. Remember, my values here are name tuples. So there's a really nice thing here where if you create a bunch of name tuples like this, it'll actually break this into a data frame. So I'll have a column for M, a column for S, and a column for LP, and it'll return a data frame to me.
Cameron, if you try to print out thread buffer, does it print it out from each thread? If you do it inside here, okay. Yeah,
so if you print it out here, you'll get 50 copies of different buffers for M threads. So each thread basically has its own access to the IO stream, and they can actually cut in front of each other as normal. So that's a little annoying. I'm going to generate some random values. So I'm going to get 100,000 data points with mean -1 and a variance of whatever 1.1 squared is. I'm going to make my grid point for the means. I'm going to say, all right, it has to be between -5 and 5 and with a length of 50. My variances, I'm going to say, are between 0.5 and 3 with a length of 50. And then I'm just going to generate the grid, which in this case, see here it is printing out each of the thread buffers. So it's just an array of name tuples. And so there should be, 50 elements in there. All right. And then the result here is in vals. Vals here is now a data frame. And then let's say I just sort these by the log probability. So the highest log probability is the maximum likelihood estimate, at least within our grid search, right? This is not perfect. It's kind of a discrete grid. So, one of the nodes in the grid is the highest point. And if I sort the data frame I got by log probability with the highest values up top, and I'll just take the first 5, we can see that the maximum likelihood estimate is -0.91 for the mean and 1.11 for the variance, which is about what I set it to. So I think that's kind of a nice little example of how you might do grid search. And it kind of showcases how you can use name tuples if you want to collect all kinds of weird information and store it and then get a data frame for free at the end. That's one of my things about kind of doing this. This is a very common paradigm for me, is where I'll multi-thread some big loop, and then I'll generate a bunch of name tuples with a ton of information, stick them on an array, and then print out a data frame at the end. All right. And then if we wanted to plot our search grid here, all I'm doing is plotting the means on the x-axis, the values on the y-axis, and the log density on the z-axis. You can kind of see this is like our likelihood surface. And so like right about here, something like right around here is our maximum likelihood estimate. Okay, cool. But I just wanted to show people a good, like a reasonable example of how you might actually use this in something a little more complicated. I'll skip this for now, threads X, but threads X is really, really good if you just want to use map. So if you put threads X, if you import threads X and you put threads X dot something in front of a base Julia function, it'll just dispatch it to whatever your threads are. So you don't have to do even threads dot at threads. So really useful if you're working in like a map reduce type situation. If you have a really big collection to iterate across. And threads X actually ends up being really, really, really fast. once it's compiled. Okay, so here it is. This is the base version of sum, and here is the threads-x version of sum. Much faster. Or, well, it scales up if I add more here. Okay. Yeah, so I wanted to show this kind of plot here. Like, I've made this kind of claim that if you have more and more data, your threading performance just kind of scales, like, by a lot. And so what I've done here is I basically compute sum, and that using, this is the base implementation of sum, and then I calculate the threads-x version of sum, and then I just scale up the size of my data, and then I calculate the difference in the times between the two. And so I wanted to show you an example of what that looks like so that you can kind of visualize how much benefit you actually get from threading performance. So here you can see that the base function, when you have very small data, the performance is very similar. But if you have like a ton of data, actually doing a threaded implementation starts to look a lot better because the gap between the base and the threaded version is much larger, right? So if a thread has to do a lot of work, it generally tends to do better than, not a serial implementation. Okay. All right, so with the 40 minutes we got left, I'm going to do multiprocessing, which is like the fun and maybe confusing one. So there's some big changes here. So instead of threads, we have processes. Processes can also have their own threads. But processes have their own memory space, which is important if you're putting these on multiple computers or you're in a cluster environment. Processing starts to look a lot better. You have to build infrastructure to make processes communicate because they don't share memory. You have to actually like build ways for them to talk to each other if that's something you need them to do. Processes are managed by the operating system. Threads are managed by Julia Scheduler. And you can just kind of have a ton of processes and it's just kind of fine. Whereas you don't want a whole bunch of threads. Julia's documentation, as ever, is also really good on this. They have a very good description of how you can kind of work in a distributed computing type solution. Okay. So multiprocessing, in my experience, is a little clunkier to work with, especially if you want to do message passing between processes. So I don't tend to do it unless I need like a lot of firepower. Like I need like a ton of processes and I have a whole bunch of hardware to work with. Then I tend to work with multiprocessing. But in general, I find that threading gets me along more or less just fine. So let's just kind of like dig in here. You can actually add processes to Julia after you start it, unlike with threads. So you can add processes by calling Julia with -p and the number of processes you want, if you want to do that ahead of time. Or you can just call add procs, distributed.add procs. And I put 4 here, so it'll add 4 processes and link them up to my main process. Okay, so when I started out, I have no processes or just one process. That is the process that is currently running everything. Now I'm going to run this one here and I'm going to add 4 processes. Actually, it'll probably add an additional 4 processes because I've already run this. So I'll have 5 processes. Okay, cool. That's perfect. Okay, so now I have 4 extra buddies that I can go ask to do stuff. All right. So if you guys remember the spawn function macro that we called, there is a similar macro called spawn at, which is used for processing or for asking processes to do stuff. So here I'm going to do task 1 here is I'm going to create, I'm going to basically ask process 2, that's the first argument to this macro, to add 1 and 1 together. And when I run this, you'll see that it creates a future with nothing in it for task 1 and task 2. And in order to get stuff out of those tasks, we're going to call fetch. So fetch just says, hey, go check inside of the future, go get me the result of that, right? So this is about the same as multi-threading. And fetch is, again, a blocking call. So it'll wait there until the future is full. Processes can be kind of annoying because you just don't understand that the other process has basically no information when it starts out. It's like a fresh Julia process. It has not compiled any function. It doesn't know any of your variables. It doesn't know anything. So you actually have to tell it, hey, I need you to compile this function. So for example, let's say I said, hey, I want to make some other process run mystery function, which is just the multiple of sine x and cosine x. Okay, and then I want to give it the input of 5. Okay, so I can run this. Nothing wrong happens here. It still generates a future. But when I try to actually get the result out using fetch, it's going to give me an exception because it says mystery function is not defined. I don't know what that is because we just made this new process. It's brand new. It's like fresh from the womb. It has no information. So we actually have to give it the function to tell it how to use it. Okay. So the fix for this is at everywhere. So if you put at everywhere before something, it will distribute all of that code to all of the processes and run them all together. Okay. So if I put at everywhere in front of mystery function, when I define it, all the other processes will now have it available to them. So when I run it, I will get an answer. Now I will get the number. Okay, so at everywhere, great. You need to tell your functions, or you need to tell your processes what to do. If you have multiple lines, you can do begin. If you want to run several expressions together. So for example, x is equal to 1, y is equal to red, my name. And then I can create a function where I just basically smush them together and create a string from x, y, and my name. Now the process has those available, so it can smush those together. Okay, so anything you want other processes to know about either has to be in the expression, like a literal expression inside of the SpawnAt call, or it has to be something it already has because everywhere was called. So if you're doing some kind of like big production thing, typically what you do is you put all of your like preamble code, everything that a process might need to know inside of a file called preamble.jl, and then just call at everywhere include. And this will run everything that's inside of that file. I'm actually going to skip the concept check here.
We already covered this, but do processes have IDs? Like, can I say execute this code?
Yeah, so if you
with an ID, blah.
Yeah, so it's incremental. So I believe it's distributed. So the main process has ID 1.
Okay.
Every process has, incremental integers. So when you call SpawnAt, you can specify an explicit process. So if you do at SpawnAt 4, it'll go to, the process with ID 4.
Because usually, like, if I write API code in my, that preamble.julia file, supposedly I can use that ID that does something different based on ID, right?
Yeah. So I think so like, let's imagine this is preamble.jl. What you could do is if distributed, there we go. Distributed.myid equals 2, proc2 stuff. And then you could have like if you knew that you were always going to assign one type of thing to process 2 and a different thing to process 3, then you can do all kinds of fun little tricks like that. I think that's how I would do that. Ooh, that's clever. I like that. Okay. Distributed actually has a pmap, parallel map function, which will basically just take all of your inputs and distribute it amongst your processes. So for example, I wrote this pfunc function here, and all it does is return the input that it had, the signed value of that input, and then whatever the ID of the process that actually calculated this answer. So you can see here, one, they're in order, which is kind of nice. And two, they've all been assigned to different processes, and here is the corresponding sign value for that input. Okay, so PMAP, super awesome. You can optionally also use @distributed. So @distributed is like the exact same as threads.@threads, but in this case, it just distributes them amongst all of your loops or all of your processes that are available. You can also create an array it's a shared array that handles MPI. So if you have like an array, you want each process to be able to add or subtract to or modify, shared arrays is a good way to do that. So in this case, I had to explicitly type it because I was adding a tuple of int, float, and int. And so they can modify each value without, causing weird copies and not having different records of the underlying array. So this is a good way of like pre-allocating something and then having each process stick whatever they need to in the right spot. Okay.
And this distributed package, it works across nodes.
Yep. So when you load, in principle, if your operating system handles just like spreading it across nodes, spinning new processes across nodes, they'll all just link up to each other correctly. There's a cluster manager thing that makes that like way easier. Like if you wanted to have like SSH interconnect between all of them, like you can do all this kind of gnarly stuff that I haven't needed to do yet. But yeah, distributed should handle multi-node comms as long as your operating system handles it well, which the Yens do, I believe.
Not the Yens, but Sherlock does.
Oh, okay, gotcha. All right, then I won't oversell Yens. Don't use the Yens, people. Use Sherlock.
If you need multi-node code, yeah.
So that brings me to like communication between processes, right? This @spawn, @pmap stuff, this will all handle, single tasks that are independent of one another. But sometimes you might have like a process that does one thing and you need to send it messages over time. You need to have like a communication channel available to it. So the common way that this is done is with a remote channel. And so a remote channel is more or less a pointer to like a little information stream of some type of thing. So for example, I'm creating a channel here, put with an exclamation point, takes whatever is the second argument and puts it into that channel. And by default, this has a buffer size of 1. So you can only put one thing in this channel. If you want to change the buffer size, it has to be an anonymous function that refers to just a channel. So for example, if I do this, channel 0, that means an unbuffered channel. So you can put as many things as you want to in this channel. If I do 10, this means there can only be 10 things inside of this channel at any point in time. If you try to put something in a full channel, so if there's 10 items inside of this channel, you'll sit there and wait until the channel gets cleared out. Okay, so that's how you can change the size of the buffer if that's something you need to do. But right now I'm just going to work with a single element channel. Okay, then I'm going to put the value 1 in it, and then take goes into the channel and pulls out whatever's available. Okay, and I believe this is FIFO channel, so first in, first out. But somebody should check that. So I'll show you how this works in kind of like a multi-process setting. I'm going to create this worker function where it's going to accept a channel. So this is the communication relay between multiple processes. It's going to create a counter, and then it's just going to loop forever. And it's going to try and see if there's something inside of the channel. If there's nothing inside of the channel, it'll block here forever. So you have to try to put something in the channel. Otherwise, this process will just be waiting and waiting and waiting and waiting for something to show up. Okay. If the value is 0, it's just going to return counter. So the way I terminate this function is by putting 0 into the channel. Once I do that, it sees this and it'll return whatever the counter is. If it's not 0, it just increments by 1. It just says, hey, I didn't get 0 this time, add 1 to counter, and then it'll go back and loop forever. Okay. You note that I'm declaring this at everywhere because I need my worker process to be aware of this function because I'm going to ask it to do this. Okay, so I'm going to create a buffered channel, and this time I'm going to type it explicitly. So because I know I'm only going to put integers into this channel, so that's a good idea for typing, because you know that anytime you do a take on this, you'll always get an integer, which is good for typing. Okay, then I'm going to take I'm going to use spawn at to create a worker that's just going to sit and wait for me to send it information. Then I'm going to put some messages into it. So first I'm going to put 5, then I'm going to put 8, then I'm going to put 0. So the first two, it's going to see that they are not 0. It's going to increment, the worker is going to increment its counter by 1. And at the end, it'll be at 2. And when it receives the 0, it'll return and it'll dump a result into the task. So remember, there's actually two forms of means of communication between my process and the worker process here. There's the channel where I can send it, we can send each other messages. And there is the future, which is the result of this task completing. So when I run this, and when I call fetch task, it'll see that it'll see counter returning too. Okay. So this is a pretty common thing that happens there as well. I found it to be not super common to do this kind of framework, this kind of like worker process framework, even though it's really nice, just because a lot of things are very homogeneous. And so you kind of don't need this like heterogeneity where like one process is queuing up work for another process. It's kind of rare. Like the only times I've used this is when I've had like a lot of terabytes of weird data, where I'll have like one process reading data and then throwing it to another process that's like bundling it up and putting it in a nice shape and throwing that somewhere else. So I don't know. I have not really seen like a compelling use case yet for this kind of framework. But if you're doing something like that, you can also have your worker process actually send results as they come along to the the main process. And you can do that by adding a second channel. So for example, now I've changed the worker to receive an input channel and an output channel. And it'll take a task and the data to do that task. And then it'll calculate whatever it's supposed to do and then put it in the results channel. And in this case, I've made the loop terminate at 100 if it just doesn't get enough tasks, because I don't really want this process spinning out forever. And yeah, so here I can just create a worker with the task channel and the result channel. Then I'm going to give it the sign function, and please calculate the value of the sign function with 1, and then cosine with 5, and then I can take both results and print them out. And there we go. So you can imagine this being a much bigger deal if you have like, huge vectors or like locations of data for the worker process to go load by itself. That's kind of another thing that you can do. So if you're doing something weird like this, I kind of want to know, or you think you'd need it, just because I think it would be cool to see what it is that you're doing. So I don't know. The only times I've done this have been like in industry when I needed to, had some like big systems programming type thing. Okay.
Can you send multidimensional arrays?
Yeah, you can send whatever you want. You can send like, just like make sure that your channel can handle it. So if you wanted to send like, for example, vectors, you do this, make sure that you actually type it correctly. You can also just do like remote channel any, which basically says, I will accept whatever you want to put into the channel. I don't recommend doing this because it's just very type unstable. It's kind of sloppy programming. If you know exactly what you're going to be piping into a channel, you should probably try and type it early. But in general, you can put whatever you want. Data frames, vectors, you can put tuples, you can put anything, which I actually really like. I find that to be quite pleasing. Okay, so any questions about multiprocessing? Like, it's pretty straightforward. Instead of threads.atthreads, it's distributed.atDistributed. Instead of spawn, it's at spawn at. And you can add processes at the very beginning of your call. All right. Any thoughts on any of that? Okay, perfect. So I'm going to kind of conclude here with GPU computing. So basically, GPUs were not intended at the start to be what they are today, right? What they were intended to do was like, render random stuff on your screen so that your CPU could do other stuff because your CPU sucked and like you didn't want it to do all this like parallel computation. So the GPU is just kind of like a side processor to make the CPU be able to work better. But the GPU is basically a CPU with way more cores. Each of these cores are like kind of worse than the cores on a CPU, but they're linked up very well such that they operate in serial or in parallel extremely well. So my graphics card is an NVIDIA RTX 2060, and I've got 1900 cores in it, which is bonkers to me. Like, it's really good. I believe it's all 32-bit cores, which is like a little annoying if you have like really high precision needs. But in general, I don't think it's going to be too much of a concern for people. So just to kind of like compare the architecture a little bit, your CPU might have like, between 1 and 8 cores, and your GPU has like a bunch of little multiprocessors that have a ton of cores inside of themselves, right? And so the GPU is able to like, you can give it a single instruction and just pump a bunch of data through, and it'll just churn out data by feeding it into this big core factory, basically. Okay. So GPU computing has become like massively useful for very parallel problems. So like some linear algebra operations are incredibly parallelizable, like linear solves, or like deep learning is a lot of like derivative computation, like batched matrix derivatives and things like that. So anytime you're working with like matrices and lots of data that you have to do the same thing to many times, GPU compute has kind of showed up and made everything way faster and cooler. So if you do not have a GPU on your machine, this might be a little hard for you to follow along. And GPUs are a lot less standardized. So if you have an AMD GPU, you will be doing different things than if you have like a CUDA compliant NVIDIA card. So NVIDIA is definitely a lot more common, and I think, at least in scientific computing, I think most people would agree with that. At least that CUDA is like pretty damn good. It's a little annoying to read the documentation, but it's still good. So the important packages here are CUDA this is like the everything you need to know. Like this should be like the one thing you import if you're working with graphics cards in an NVIDIA card. There's an AMD GPU. If you work in differential equations, which I like to point out in Julia, there is like a very good package for doing differential equation solvers boosted with GPUs. And they have a couple of methods that have been implemented, even heterogeneous, like cluster GPU computing, which is really nice. So this is kind of a good example about how to do really good GPU compute, but I'm not going to be showing it to you today. Okay, so what do you use them for? What do you use these GPUs for? And the answer is a pretty good one, which is GPU programming is a huge pain in the ass if the second you have to do anything mildly complicated. However, when they're in a very nice little well-defined problem space, they're incredibly fast and very easy to use. So the best way to use them is to stick to well-defined problems. So if you're doing any kind of well-defined linear algebra stuff, multiplication, dot products, whatever, you just like basically wrap all of your data in a CUDA array, and it'll go through automatically, and you'll get free speed. So that's like super awesome. I'll leave this off to the side, but basically there's probably a function that does like a really simple operation on some kind of CUDA array, which is just like a Julia's way of representing arrays inside of your GPU. So I'm going to show you some examples of how you can just like use this. So I'm going to import CUDA. And if you, or CUDA, I think it's CUDA. I think people say CUDA. But basically what I'm doing is I'm going to draw a bunch of random numbers, 10K by 10K, and using the CUDA version of this function wraps it up in an array, a CUDA array. So for example, I can print line, I'll print out the type of X, and we'll see that it's a CUDA array. And I'll do that for Y as well. Then I'm going to do X underscore H, and I'm just going to call array on whatever X is. And that takes the CUDA, the stuff that's living in my graphics card, the array that's in my graphics card, and moves it over to my machine. So this is an expensive operation. You don't want to be doing this all the time. If you can leave it inside of your graphics card, try and leave it there, because going in between the host machine and your graphics card is expensive. And then I'm just going to do dot products with the regular Julia version of the array and then the X array. And you can ignore this error because I have worker processes and they get mad when I do linear algebra. Okay. So we can see that the type is a CUDA array. You'll note that it's 32-bit precision, which is maybe a little odd to you, but just be aware that that's what's going to happen when you're going to use graphics cards. And we can see that the CUDA dot product is so much faster. It's like hilariously faster to do the dot product. We can do it with linear solves. You'll note that the syntax is identical, right? You don't have to change anything. So if you just pass in two CUDA arrays on either side of this normal linear algebra functions, you'll just get the CUDA stuff for free. Oh no, yeah, this is wrong. This is the other way. This is the host machine. Yeah, there it is. That's the performance I was expecting. Okay. Damn compilation time. So in this case here, the linear solve is just the backslash operator. And that is also extremely fast. So it's, 5 or 6-ish times faster. The Koleski decomposition, if that's something you work with a lot, that's also very well parallelized and well defined. I'm not even going to run the eigenvalue solver, because as you can see, the last time I ran this, the CUDA version of this is almost 8 seconds. The serial version of this is 438 seconds, just to get the eigenvalue pairs for this 10K by 10K matrix. So if you have like huge arrays of data and linear algebra operations you want to do, just try wrapping it in a CUDA array. And the way you can do that is, like, let's say I had like 100,000, 10,000. So like, let's say you had created an array that was 10K by 10K. Let's say you had loaded this from a data frame, like from a CSV file, or like from some other storage format, or you'd created it through simulation, something that was CPU compute. And then you had to do like a bunch of like big linear algebra operations on it. You can basically just do, I believe it's CU. And now you have a CUDA array. So anytime now that you do, a set of well-defined linear algebra operations between two CUDA arrays, you'll get the free CUDA speed. Okay, so like anytime you're working in that kind of environment, maybe a good idea to consider just calling CU on an existing array and then doing whatever it is that you want to do with that array. Okay, so that's like a really cool thing where sometimes, for a lot of code that you roll yourself, you can just put it in a CUDA array and it'll just go to your GPU without you thinking about it, just through the wonders of multiple dispatch, because there's a bunch of dispatched methods on CUDA arrays rather than regular arrays. Okay, the one thing don't do is XCU. So it does not like it when you try to invert CUDA arrays. Just because it's kind of like, it's hard to do, like doing the multi-threaded inverse of something is like not really a thing. There's a couple solvers that you can do, but you kind of have to go root around in the incredibly annoying documentation for CU solver and CU BLAS. So like you have to like go and like read this like truly ugly documentation about weird command codes for like random solvers in CUDA. So once you start getting into like outside of like eigen and invert dot and transpose and multiplication and stuff like that, it starts getting a little annoying. Like you can kind of see an example of it here where I calculated the eigenvalue, right? I actually had to go into CU solver and call the function that just is a wrapper around the C function, right? So this is just, there's a function HEVD in CU solver. Which this one talks to, which is super annoying, right? HEVD, which is super annoying. So anytime you're working with like kind of non-standard functions, you might have to root around in CUDA functions, which is a little annoying, but sometimes it's worth it. Okay, that's kind of all I had for right now. I was going to do the project, but I think I'll kind of like put it off to the side for now. The project, if you are watching the video later and wanted to go through it, is basically to take this code that is in the Julia Bootcamp 2022 repo and just make it and just parallelize it. So permit somebody to say, yes, I would like to do this multi-process, or yes, I would like to do this multi-threaded, and then just make it easy for them to kind of parallelize their bootstrapping code. Okay. Alrighty. Thank you very much. I think we can kind of probably pause the recording here unless people have like questions about like GPU stuff.
Thank you.